In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. Exploring 51 Pegasi b, the first exoplanet around a sun-like star. Before 1995, we knew of only one planetary system in the entire universe, our own. For centuries, we wondered, are we alone? Do other stars have planets? Then, on October 6, 1995, everything changed. Welcome to 51 Pegasi b, the planet that revolutionized astronomy and forever altered our place in the cosmos. The discovery that shook astronomy. Our story begins at the Haut-Provence Observatory in the hills of southern France. Here, two Swiss astronomers, Michel Mayor and Didier Queloz, were conducting what seemed like routine observations. They were using a specialized instrument called the LED spectrograph, a tool designed to detect the tiny wobbles in a star's motion. The technique is called the radial velocity method, and it's based on a beautiful principle. Planets don't just orbit stars, they dance together. A planet's gravity tugs on its star, causing it to wobble ever so slightly. By measuring these wobbles through the Doppler shift in the star's light, astronomers could detect the presence of unseen planets. What Mayor and Queloz found orbiting the star 51 Pegasi was shocking. The data showed a massive planet, roughly half the mass of Jupiter, completing an orbit in just 4.2 Earth days. This was impossible according to everything astronomers thought they knew about planetary systems. The astronomical community was skeptical. Some dismissed it as instrumental error. Others suggested the signal might be caused by stellar activity rather than a planet. After all, gas giants weren't supposed to exist close to their stars. In our solar system, Jupiter takes nearly 12 years to orbit the Sun. How could a similar planet orbit its star in just 4 days? But within months, other observatories confirmed the finding. The planet was real. And with that confirmation came a stunning realization. Our theories about how planetary systems form were fundamentally incomplete. The universe, it seemed, was far more creative than we had imagined. 24 years later, in 2019, Michel Mayor and Didier Queloz were awarded the Nobel Prize in Physics for this discovery, a discovery that opened the door to a new era in astronomy. Today, we know of over 5,000 exoplanets. But all started here with 51 Pegasi b, a world of extremes. So what is 51 Pegasi b? Let's journey to this alien world and explore what makes it so extraordinary. Located approximately 50 light-years from Earth in the constellation Pegasus, 51 Pegasi b orbits a star remarkably similar to our own Sun, though slightly smaller, slightly cooler, and slightly older. If you could see this star from Earth with the naked eye, it would appear as a modest fifth-magnitude star, just visible under dark skies. 51 Pegasi b belongs to a class of planets, now known as hot Jupiters. Like Jupiter, it's a gas giant, a world with no solid surface, composed primarily of hydrogen and helium. It has about half of Jupiter's mass, but is significantly puffed up by the intense heat from its nearby star, making it physically larger than Jupiter despite being less massive. But here's where things get extreme. While Jupiter orbits the Sun at a distance of about 500 million miles, 51 Pegasi b orbits its star at just 5 million miles, closer than Mercury is to our Sun. Its orbital period? Just 4.2 Earth days. Imagine experiencing a year in less than a week. This proximity to its star creates hellish conditions. The day side of 51 Pegasi b reaches temperatures of approximately 1,000 degrees Celsius. That's 1,800 degrees Fahrenheit. hot enough to melt most metals, hot enough to vaporize rock. Like our moon is to Earth, 51 Pegasi b is likely tidally locked to its star. One hemisphere eternally faces the scorching starlight, baked in perpetual day. The other side, forever in darkness, may be somewhat cooler, though powerful winds likely redistribute heat around the planet, creating a complex and violent atmospheric circulation pattern. What would it be like to descend through the atmosphere of 51 Pegasi b? While we can't send a probe there, not yet, at least, modern spectroscopy allows us to analyze the starlight filtering through the planet's atmosphere as it transits across its star. These observations reveal a world utterly alien to our experience. The extreme temperatures create atmospheric conditions unlike anything in our solar system. Scientists theorize that 51 Pegasi b might have clouds, but not the water vapor clouds we know on Earth. Instead, imagine clouds made of vaporized metals, sodium, potassium, perhaps even iron and silicates condensing into tiny droplets. On the cooler night side, these metals might rain back down as liquid metal precipitation before evaporating again on the scorching day side. The atmosphere is constantly in motion. Supersonic winds, possibly reaching speeds of several miles per second, race around the planet, driven by the extreme temperature difference between day and night. These winds carry heat from the day side to the night side, creating a tumultuous, ever-changing environment. There might be lightning storms of unimaginable intensity, and perhaps auroras created by the star's stellar wind interacting with the planet's magnetic field, if it has one. Every aspect of this world pushes the boundaries of what we thought possible for a planet. The discovery of 51 Pegasi b didn't just add one planet to our cosmic census. It forced us to completely rethink how planets form. According to the prevailing theory before 1995, planets form from a disk of gas and dust surrounding young stars. Close to the star, where it's hot, only rocky materials can condense. Further out, beyond what's called the frost line, it's cold enough for ice to form. These ices, along with rock, provide the building blocks for gas giants like Jupiter. In this model, gas giants always form far from their stars, where there's enough solid material to build a massive rocky core, typically 10 to 20 times Earth's mass. Once this core is large enough, it can gravitationally capture huge amounts of hydrogen and helium gas, creating a Jupiter-like world. So how did 51 Pegasi b end up so close to its star? It certainly couldn't have formed there. The answer lies in a process called planetary migration. We now understand that planets don't necessarily stay where they form. Young planets interact with the disk of gas and dust around their star. These gravitational interactions can cause planets to spiral inward, migrating toward their star over millions of years. 51 Pegasi b likely formed much farther from its star, perhaps where Jupiter is in our solar system, and then migrated inward to its current scorching orbit. This discovery revolutionized planetary science. We now know that hot Jupiters, once thought impossible, are actually quite common. They make up about 1% of known exoplanets, and their existence tells us that planetary systems are far more dynamic and diverse than we ever imagined. Each one is a unique laboratory for understanding how planets form, evolve, and interact with their stars. Could there be life on 51 Pegasi b? Almost certainly not. The extreme heat, crushing pressures, and lack of solid surface make it inhospitable to any form of life we can imagine. But here's the profound truth. 51 Pegasi b didn't need to be habitable to change everything. Its discovery proved that planets are common in our galaxy, that our solar system isn't unique or special. And if planets are common, then potentially habitable planets might be common too. The radial velocity method pioneered by Mayer and Culo opened the floodgates. Within a few years, dozens of exoplanets were discovered, then hundreds, then thousands. Today's planet hunters use an arsenal of techniques. The transit method, which detects the tiny dimming when a planet passes in front of its star, direct imaging, which actually photographs planets, and gravitational microlensing, which uses Einstein's general relativity to detect planets around distant stars. We've discovered planets of every conceivable type. Super-Earths larger than our planet, but smaller than Neptune. Mini-Neptunes, ice giants, lava worlds where the surface is an ocean of molten rock, and yes, rocky planets orbiting in the habitable zones of their stars, where liquid water could exist on the surface. Modern telescopes like the James Webb Space Telescope are now analyzing the atmospheres of these distant worlds, searching for biosignatures, chemical signs that might indicate the presence of life. We're looking for oxygen, methane, water vapor, and other molecules that, in the right combinations, could suggest biological processes. Future missions are already in development. Telescopes specifically designed to image Earth-like planets directly, to study their atmospheres in unprecedented detail, and perhaps, just perhaps, to find evidence that we are not alone. From a single discovery in 1995 has grown an entire field of science. Thousands of researchers around the world now dedicate their careers to studying exoplanets, worlds that didn't even have a confirmed existence just 3 decades ago. Every new discovery raises new questions. Why are some planetary systems so different from ours? How common are planets like Earth? What fraction of stars have planets in their habitable zones? And the question that captivates us most, how many of these worlds might harbor life? We don't yet know the answers, but we're closer than ever to finding out. Every telescope, every observation, every discovery brings us one step closer to understanding our place in this vast cosmos. B, officially designated Dimidium, meaning half in Latin, reflecting its half-Jupiter mass, will forever hold a special place in human history. It's the planet that proved we weren't looking at a lonely universe, but one teeming with worlds beyond our imagination. Small blue world, we gaze out at the stars and wonder. We build telescopes and train them on distant suns. We ask questions that previous generations could only dream about. And we search for planets, for signs of life, for answers to the deepest questions we can ask. The next time you look up at the night sky and find the constellation Pegasus, remember, orbiting one of those distant stars is a world that changed everything. A planet that opened our eyes to the cosmic truth that we live in a universe of countless worlds. 51 Pegasi B taught us that the universe is far stranger, far more diverse, and far more wonderful than we ever imagined. And the greatest discoveries? They're still waiting to be made. Next, let's journey to Proxima Centauri b, our closest exoplanetary neighbor. Look up at the night sky. Among the thousands of stars visible to the naked eye, one stands out, not because it's the brightest, but because it's the closest. Just 4.24 light-years away, Proxima Centauri, a small red dwarf star, is our nearest stellar neighbor. And orbiting that star is a world that may hold the key to one of humanity's greatest questions. Are we alone? Welcome to Proxima Centauri b, a rocky planet, possibly similar to Earth, orbiting in the habitable zone of the closest star to our Sun. This is the story of our nearest exoplanetary neighbor, a world that could harbor life just 4 light-years from home. For decades, astronomers wondered, does our nearest stellar neighbor have planets? It seems like such a simple question, but Proxima Centauri, also known as Proxima or Alpha Centauri c, is a challenging target. Proxima Centauri is what's called a red dwarf, the most common type of star in our galaxy, yet dramatically different from our Sun. It's just 1/8 the mass of our Sun and only slightly larger than Jupiter. It's so small and dim that despite being our closest neighbor, you need a telescope to see it at all. In 2016, a team of astronomers led by Guillaume Anglade launched a campaign called Pale Red, a deliberate echo of Carl Sagan's famous pale blue description of Earth. Using the HARP spectrograph at the European Southern Observatory in Chile, they monitored Proxima Centauri with unprecedented precision. They were using the same radial velocity method that discovered 51 Pegasi b 2 decades earlier, searching for the telltale wobble that betrays a planet's gravitational influence on its star. Night after night, they collected data measuring velocities precise to within 1 meter per second, slower than a walking pace. And then there it was, a clear periodic signal. Every 11.2 days, Proxima Centauri wobbled ever so slightly. The cause? A planet with a minimum mass of at least 1.17 times that of Earth, orbiting at a distance of just 7.5 million kilometers, 5% of the distance between Earth and the Sun. The announcement on August 24th, 2016, made headlines around the world. Scientists had discovered a potentially rocky planet orbiting in the habitable zone of the closest star to our solar system. For the first time, the nearest exoplanet wasn't hundreds or thousands of light years away. It was right next door, cosmically speaking. Follow-up observations in subsequent years confirmed and refined the discovery. In 2020, additional data strengthened the case, and astronomers began to suspect there might be other planets in the system as well. But Proxima Centauri b remained the star of the show, the closest potentially habitable world beyond our solar system. So what is Proxima Centauri b? Let's journey to this nearby world and explore what we know and what we can only imagine. Proxima Centauri b is likely a rocky planet, what astronomers call a terrestrial world, similar in composition to Earth, Venus, or Mars. With a minimum mass of 1.17 Earth masses, it could be anywhere from 1 to 1.8 Earth masses depending on the angle of its orbit that we can't directly observe. It's possibly similar in size to Earth, though it could be somewhat larger. But here's where things get interesting and strange. Proxima b orbits its star at just 7.5 million kilometers, or 4.6 million miles. That's closer than Mercury is to our Sun, which orbits at 58 million kilometers. It completes one orbit its entire year in just 11.2 Earth days. You might think that being so close to its star would make Proxima be a scorched, lifeless world. But here's the crucial difference. Proxima Centauri is a red dwarf, much cooler and dimmer than our Sun. It radiates only about 0.17% of the Sun's energy. At this close distance, Proxima b receives roughly the same amount of energy from its star that Earth receives from the Sun, placing it squarely within the habitable zone, the region where liquid water could exist on a planet's surface. If Proxima b has an atmosphere similar to Earth's, its average surface temperature could be around minus 39 degrees Celsius or minus 38 Fahrenheit, cold, but not impossibly so. With a thicker atmosphere or greenhouse warming, it could be significantly warmer. The question isn't whether it's the right distance from its star. It is. The question is whether conditions on the planet allow for habitability. As a rocky planet, Proxima b likely has a similar internal structure to Earth, an iron core, a rocky mantle, and a solid crust. But we don't yet know its exact composition. Does it have a magnetic field like Earth's, which shields our planet from harmful radiation? Does it have plate tectonics, which on Earth help regulate the climate and recycle nutrients? We simply don't know yet. Living next to a red dwarf star comes with unique challenges. Challenges that may make the difference between a habitable paradise and a barren wasteland. Proxima Centauri is what astronomers call an active star. It's young, about 4.85 billion years old, similar to our Sun. But unlike our relatively calm Sun, Proxima regularly unleashes powerful stellar flares and coronal mass ejections. These violent eruptions can increase the star's brightness by a factor of 10 or more in just minutes, bathing any nearby planets in intense radiation. In March 2016, just months before the planet's discovery was announced, astronomers observed a massive flare from Proxima Centauri. For 10 seconds, the star's brightness increased by a factor of 68 in X-ray wavelengths. Such an event would deliver a radiation dose thousands of times higher than the largest solar flares that reach Earth. And these super flares may occur several times per year on Proxima. On Earth, we're protected from solar radiation by our magnetic field, which deflects charged particles, and our thick atmosphere, which absorbs harmful radiation. But does Proxima b have these protections? If the planet lacks a strong magnetic field, stellar flares could strip away its atmosphere over time, leaving it airless and uninhabitable, much like Mars. There's another challenge: tidal locking. At such a close orbital distance, Proxima b is almost certainly tidally locked to its star, just as our moon is tidally locked to Earth. This means one side of the planet permanently faces the star, bathed in eternal daylight, while the other side is locked in perpetual darkness. Imagine a world divided. On the day side, the star hangs motionless in the sky, perhaps appearing about 3 times larger than our sun appears from Earth, glowing a deep red. The temperature might be warm, possibly even hot. On the night side, Proxima Centauri never rises. The sky is forever dark, filled only with distant stars. The temperature plummets, potentially cold enough to freeze carbon dioxide. Could life survive on such a world? Surprisingly, the answer might be yes. Computer models suggest that if Proxima b has a thick enough atmosphere, powerful winds would circulate heat from the day side to the night side, moderating the temperature extremes. There might be a terminator zone, the twilight region between eternal day and eternal night, where conditions are most temperate. If the planet has oceans, they would play a crucial role in heat distribution, just as they do on Earth. The day side might have a large ocean with a substellar point, directly beneath the star, where water is warmest. The night side could be covered in ice, but underneath, a global ocean might remain liquid, protected by an insulating ice sheet. The most fundamental question about Proxima Centauri b is this: does it have an atmosphere? Everything else, habitability, liquid water, the possibility of life, depends on the answer. There are several possibilities. Proxima b could have a thick atmosphere rich in greenhouse gases, keeping the planet warm despite its dim star. It could have a thin atmosphere like Mars, unable to sustain liquid water on its surface. Or it could have no atmosphere at all, stripped away by billions of years of stellar flares. A dead world, airless and frozen. Detecting an atmosphere around Proxima b is one of the greatest challenges in modern astronomy. The planet doesn't transit across its star from our perspective, meaning we can't use the standard method of analyzing starlight filtering through its atmosphere during a transit. Instead, astronomers must use other techniques, searching for the planet's faint reflected light or its thermal emission. In recent years, astronomers have attempted to detect signs of an atmosphere using some of the world's most powerful telescopes, including the James Webb Space Telescope. So far, the results have been inconclusive. Some studies suggest the planet may lack a substantial atmosphere. Others leave the question open. The search continues. Scientists have also conducted laboratory experiments and computer simulations to understand what kind of atmosphere Proxima b might have retained despite its star's harsh radiation. Some models suggest that if the planet formed with enough water, several Earth oceans worth, it might have sustained a steam atmosphere for millions or even billions of years, eventually cooling into a water world with a thick atmosphere. Other scenarios are equally plausible. Proxima b could be an ice world, frozen solid beneath a thin atmosphere. It could be a scorched desert, having lost its water to space long ago. Or it could be something in between, a planet with large ice caps at the poles or on the night side, and liquid water in equatorial regions or in a substellar ocean beneath the ever-present star. If Proxima b does have an atmosphere and liquid water, Could it harbor life? This is where the search becomes truly exciting. Astronomers are developing techniques to search for biosignatures, chemical signs of life, in the atmospheres of distant planets. On Earth, the combination of oxygen and methane in our atmosphere is a strong indicator of life, as these gases would quickly react with each other if not constantly replenished by biological processes. Life on Proxima b, if it exists, would need to be hardy. It would need to survive or shelter from intense radiation during stellar flares. It would need to adapt to a tidally locked world with extreme temperature differences. But life on Earth has proven remarkably resilient, thriving in the most extreme environments, from the frozen deserts of Antarctica to the boiling hydrothermal vents at the bottom of the ocean. Could similar life exist on Proxima b? We don't yet know, but the possibility is tantalizing. Proxima Centauri b is our closest exoplanetary neighbor, but close is a relative term in the cosmos. At 4.24 light-years away, it's still an almost unimaginable distance, about 40 trillion kilometers or 25 trillion miles. To put this in perspective, Voyager 1, the fastest spacecraft ever launched by humanity, is currently traveling at about 17 kilometers per second. At that speed, it would take more than 75,000 years to reach Proxima Centauri. Clearly, if we want to explore this nearby world within a human lifetime, we need a radically new approach. Enter Breakthrough Starshot, one of the most ambitious space exploration projects ever conceived. Announced in 2016, the same year Proxima b was discovered, Starshot aims to send tiny spacecraft to our nearest stellar neighbors at a significant fraction of the speed of light. The concept is elegantly simple but technologically challenging. Imagine a spacecraft the size of a postage stamp, weighing just a few grams, equipped with cameras, sensors, and a communication system. Attached to this nanocraft is a light sail, a large, ultra-thin reflective sheet, perhaps a few meters across. On Earth, a massive array of ground-based lasers, perhaps hundreds or thousands of them, working in unison, would focus their beams on the light sail. The photons from these lasers would push against the sail, accelerating the nanocraft to incredible speeds. Within minutes, the craft would be traveling at 20% of the speed of light, fast enough to reach Proxima Centauri in just 20 years. Imagine it, a fleet of these tiny spacecraft, each one a marvel of miniaturization, racing across the vast emptiness of interstellar space. They would pass by Neptune's orbit in just hours. In a few days, they'd leave the entire solar system behind. And 2 decades later, a single generation, they would arrive at Proxima Centauri. As they approach, their tiny cameras would snap photographs of Proxima b, capturing the first close-up images of another potentially habitable world. Is there an atmosphere? Oceans? Clouds? Continents? For a brief moment during their flyby, traveling at tens of thousands of kilometers per second, these robotic explorers would give us our first real glimpse of our nearest neighbor. Then they would continue on, carrying humanity's message into the cosmic beyond. The data, images, atmospheric readings, magnetic field measurements will be transmitted back to Earth using tiny lasers. 4 years later, traveling at the speed of light, those signals would reach Earth. Scientists would gather to receive the first transmissions from another star system. It would be a moment as historic as the first photographs from the Moon or Mars, but far more profound. Our first interstellar reconnaissance mission, successful. Of course, the challenges are immense. Building a spacecraft that can survive the journey, including the intense acceleration and the impact from interstellar dust particles traveling at relativistic speeds. Creating a light sail thin enough to be light but strong enough to withstand the laser's intensity. Developing a laser array powerful enough to push the craft, yet precise enough to focus on a target just meters across. And miniaturizing cameras, sensors, and communications equipment to fit on a chip-sized spacecraft. These challenges are not insurmountable. They're engineering problems, requiring ingenuity, resources, and time. The technology is advancing. Proof-of-concept tests are underway, and the target, Proxima Centauri b, waits patiently, our nearest potentially habitable world, beckoning us to explore. Proxima Centauri b is one world among thousands of known exoplanets, but its proximity makes it uniquely important for science. Red dwarf stars like Proxima Centauri make up about 75% of all stars in our galaxy. If planets orbiting red dwarfs can be habitable, if they can maintain atmospheres despite stellar flares, if they can host life despite being tidally locked, then potentially habitable worlds might be incredibly common in our galaxy. There could be tens of billions of worlds like Proxima b in the Milky Way alone. And Proxima b isn't alone. Astronomers have discovered numerous potentially habitable planets around red dwarf stars. The TRAPPIST-1 System, just 40 light-years away, has 7 Earth-sized planets, 3 of them in the habitable zone. LHS 1140b, 49 light-years distant, may be a water world with a thick atmosphere. Proxima b is simply the closest example of what may be a very common type of world. Its proximity makes it an ideal target for the next generation of space telescopes. Future observatories, designed specifically to image and characterize exoplanets, will likely focus their attention on Proxima b. Each observation will teach us something new about rocky planets around red dwarfs, about habitability in extreme environments, and about the diversity of worlds in our galaxy. Studying Proxima b also helps us understand our own planet. Earth wasn't always the blue, life-covered world we know today. It went through stages: a hot, molten beginning, a period when it may have been completely frozen, eras when the atmosphere was poisonous to most modern life. By studying other rocky planets at different stages of their evolution, we learn about the processes that make a planet habitable or uninhabitable. Throughout history, humans have been explorers. We've crossed oceans, climbed mountains, journeyed to the poles, and ventured into space. We explore not just for practical reasons, but because it's fundamental to who we are. We want to know what's over the horizon, what's on the other side of the ocean, what's on other worlds. Proxima Centauri b represents the next horizon. It's our nearest exoplanetary neighbor, a world that might, just might, harbor life. Even if it doesn't, even if it's a barren rock, studying it answers fundamental questions about how planets form, evolve, and die. It tells us about the conditions necessary for life and helps us understand how rare or common habitable worlds might be. For children growing up today, Proxima Centauri b is more than an abstract concept. Within their lifetimes, we may know definitively whether it has an atmosphere, whether it has water, perhaps even whether it has life. If the Breakthrough Starshot mission succeeds, they'll see the first images from another star system before they're middle-aged. This isn't science fiction. It's the reality of the world they're inheriting. The search for life beyond Earth is more than a scientific endeavor. It's a philosophical quest that touches on the deepest questions we can ask. Are we alone in the universe? Is life rare or common? Is Earth unique, or is it one of countless living worlds? The answer to these questions will fundamentally change how we see ourselves and our place in the cosmos. 4.25 light-years away, close enough that light from Proxima Centauri left its star before the last presidential inauguration and is just now reaching our eyes, orbits a world that may hold answers to our deepest questions. We don't yet know if Proxima Centauri b is a living world, a frozen wasteland, or something in between. We don't know if it has oceans, continents, or clouds. We don't know if life has ever emerged there, if it exists now, or if the planet is barren and dead. But we're searching. With every new telescope, every new mission, every new observation, we come closer to understanding our nearest neighbor. We're developing the technology to image its surface, to analyze its atmosphere, and perhaps one day to send probes that will fly past and capture the first close-up images of another potentially habitable world. Proxima Centauri b reminds us that the universe is vast, filled with mysteries waiting to be solved and worlds waiting to be explored. It reminds us that the greatest discoveries often lie not in the most distant reaches of space, but right in our cosmic backyard. Whether Proxima b is teeming with life or utterly barren, it has already changed us. It has shown us that potentially habitable worlds exist around even the smallest, dimmest stars. It has given us a target for our first interstellar mission, and it has reminded us that we live in a galaxy of worlds, many of them stranger and more wonderful than we ever imagined. So, the next time you look up at the southern night sky, if you're fortunate enough to live where you can see Alpha Centauri, remember that one of those points of light is Proxima Centauri, and orbiting that star, just 4 light years away, is a world that may answer the question that has haunted humanity since we first looked up at the stars and wondered, are we alone? If you thought one planet was cool, let's now work on unveiling the TRAPPIST-1 System, a treasure trove of exoplanets. Proxima Centauri b showed us that potentially habitable worlds exist right in our cosmic neighborhood. But what if, instead of one possibly habitable planet, we found an entire system, 7 Earth-sized worlds orbiting a single star, 3 of them in the habitable zone? What if we discovered not just a world, but a treasure trove of planets that could harbor life? Just 40 light years away lies one of the most extraordinary discoveries in the history of astronomy, a star system that has redefined what's possible. Welcome to TRAPPIST-1, where 7 worlds dance in cosmic harmony, and where the search for life beyond Earth has found its most promising hunting ground. Picture this: 7 rocky planets, all roughly the size of Earth, orbiting so close to each other that if you stood on one world, you could see the others hanging in the sky, some appearing larger than our moon appears from Earth. This isn't science fiction. This is TRAPPIST-1, the most compact planetary system ever discovered, and perhaps the most important star system in humanity's search for life beyond our solar system. Discovered in 2017, the TRAPPIST-1 system shattered our expectations. Not just one potentially habitable planet, but 3. Not just one Earth-sized world, but 7. Packed into a space smaller than the distance between Mercury and our Sun, these planets orbit a star so small and cool that it barely qualifies as a star at all. Our story begins in 2015 at the TRAPPIST telescope. That's the Transiting Planets and Planetesimals Small Telescope, perched on a mountaintop in Chile. This modest 60-centimeter telescope was specifically designed to hunt for exoplanets around the smallest, dimmest stars, the ultra-cool dwarf stars. Belgian astronomer Michael Gillen and his team were monitoring a star called 2MASS J 2306-2928-0502-285, mercifully renamed TRAPPIST-1 after their telescope. It was an unprepossessing target, a red dwarf star just 8% the mass of our Sun, barely larger than Jupiter, and so dim that despite being only 40 light years away, you need a telescope to see it at all. They were using the transit method, watching for the telltale dimming that occurs when a planet passes in front of its star from our perspective. And what they found exceeded their wildest dreams. The star didn't just dim once or twice. It dimmed repeatedly, in a complex pattern suggesting multiple planets with different orbital periods. By May 2016, Gillen's team had identified 3 planets, but they suspected there were more, many more. They called in reinforcements. NASA's Spitzer Space Telescope, orbiting Earth and equipped with infrared sensors ideal for observing cool red dwarfs, was tasked with monitoring TRAPPIST-1 continuously for 20 days in late 2016. The results were spectacular. The data revealed not 3 planets, but 7, all of them roughly Earth-sized, all transiting their star in a complex gravitational dance. It was the most planets ever found in a single system using the transit method, and the most Earth-sized planets ever discovered around a single star. On February 22, 2017, NASA held a press conference to announce the discovery. The news made headlines around the world. Scientists, science fiction writers, and dreamers everywhere were captivated by the same question. Could any of these worlds harbor life? In the years since, dozens of telescopes have studied TRAPPIST-1, each observation adding to our understanding. We've measured the planets' masses, estimated their densities, determined their orbital resonances, and begun the painstaking work of analyzing their atmospheres. Every new piece of data brings us closer to answering the fundamental question, are we alone? To understand the TRAPPIST-1 planets, we must first understand their star, a celestial object so different from our Sun that it challenges our very definition of what a star should be. TRAPPIST-1 is what astronomers call an ultra-cool dwarf star, even smaller and cooler than typical red dwarfs. With just 8% of the Sun's mass and 11% of its radius, it's barely larger than Jupiter. Its surface temperature is a mere 2,550 degrees Celsius, compared to our Sun's 5,500 degrees. It's so cool that it glows primarily in infrared wavelengths. If you could see it up close, it would appear deep red, almost brown. This diminutive star produces only 0.05% of the Sun's energy. To receive the same amount of warmth that Earth gets from the Sun, a planet would need to orbit TRAPPIST-1 at about 6 million kilometers, closer than Mercury orbits our Sun. And that's exactly where the TRAPPIST-1 planets are found. The 7 planets of TRAPPIST-1 orbit in a remarkably compact configuration. Let me introduce them from innermost to outermost. TRAPPIST-1b, C, D, E, F, G, and H. The entire system would fit comfortably within Mercury's orbit. In fact, if you scale the TRAPPIST-1 system up to the size of our solar system, all 7 planets would still orbit closer to the Sun than Venus does. TRAPPIST-1b, the innermost planet, completes an orbit in just 1.51 Earth days. It orbits at a distance of only 1.7 million kilometers, so close that if you could stand on its surface, TRAPPIST-1 would dominate the sky, appearing about 10 times wider than our Sun appears from Earth. The surface temperature is likely around 400 degrees Fahrenheit, too hot for liquid water. TRAPPIST-1c orbits every 2.42 days at 2.2 million kilometers. Still too hot for habitability, with estimated temperatures around 200 degrees Fahrenheit, but recent observations suggest it may have a thin atmosphere or possibly no atmosphere at all. TRAPPIST-1d, with a 4.05-day orbit at 3.3 million kilometers, is intriguing. It's the lightest of the 7 planets, with just 30% of Earth's mass. Scientists theorize it might be a low-density world, possibly with a substantial atmosphere or even a global water ocean. Now we arrive at TRAPPIST-1e, perhaps the most Earth-like planet in the system. Orbiting every 6.10 days at 4.3 million kilometers. It has 92% of Earth's radius and 77% of Earth's mass. Its density suggests an Earth-like rocky composition with an iron core. Most importantly, it sits comfortably in the habitable zone, where temperatures could allow liquid water on the surface. If any world in this system resembles Earth, it's TRAPPIST-1e. TRAPPIST-1f orbits every 9.21 days at 5.7 million kilometers. Also in the habitable zone, it's slightly cooler than TRAPPIST-1e and might be covered in water ice, though with the right atmospheric conditions, liquid water could exist. Its size is remarkably close to Earth's, about 4% larger. TRAPPIST-1G, with a 12.35-day orbit at 6.7 million kilometers, is the largest of the 7 planets, about 13% larger than Earth and 30% more massive. It's on the outer edge of the habitable zone, likely quite cold, but potentially warm enough for liquid water with significant greenhouse warming. Finally, TRAPPIST-1H, the outermost planet, orbits every 18.77 days at 9.1 million kilometers. It's the most mysterious of the 7, the coldest, the least studied, and the one about which we know the least. Surface temperatures might be around minus 200 degrees Fahrenheit, making it more like a frozen ice ball than a habitable world. What makes this system truly extraordinary is not just the number of planets, but their orbital configuration. The planets are locked in what's called orbital resonance, a gravitational relationship where their orbital periods form simple mathematical ratios. For example, for every 8 orbits TRAPPIST-1b completes, TRAPPIST-1c completes 5, and TRAPPIST-1d completes roughly 3. This resonance chain extends through most of the system, like a cosmic symphony where each planet is an instrument playing in perfect harmony. This resonance tells us something profound. These planets likely formed farther from their star and then migrated inward together, maintaining their gravitational relationships. It's a delicate dance that has persisted for billions of years, and it makes the TRAPPIST-1 system one of the most dynamically interesting planetary systems ever discovered. 3 planets, TRAPPIST-1e, F, and G, orbit within the star's habitable zone. But what does that really mean? And what are the chances that these worlds actually harbor life? The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Water is essential for life as we know it, so finding liquid water on another world would be a crucial first step in finding life. But there's a catch. Whether a planet actually has liquid water depends on more than just its distance from a star. It depends on whether the planet has an atmosphere, what that atmosphere is made of, and how thick it is. A thick atmosphere with greenhouse gases can warm a planet far beyond what its distance from the star would suggest. A thin atmosphere, or no atmosphere at all, and the planet freezes. Consider TRAPPIST-1e, the most promising candidate. Computer models suggest that with an Earth-like atmosphere, surface temperatures could range from minus 20 to 20 degrees Celsius. Cold, but well within the range that allows liquid water. The planet could have oceans, continents, perhaps even a water cycle with clouds and rain. It might look remarkably similar to Earth. But other scenarios are equally possible. TRAPPIST-1e could be a snowball, a frozen world where water exists only as ice. It could be a water world, a planet with no continents, covered entirely by a deep global ocean. Or it could be Venus-like, with a thick atmosphere creating runaway greenhouse heating, making the surface hot enough to melt lead. One crucial clue comes from measuring the planet's densities. By knowing both mass and size, we can estimate what the planets are made of. The TRAPPIST-1 planets have densities slightly lower than Earth's, suggesting they might contain significant amounts of water, perhaps 5% by mass, compared to Earth's less than 0.1%. If these planets are water-rich, the water might not all be on the surface. Some models suggest that TRAPPIST-1 planets could have vast subsurface oceans beneath icy shells, similar to Jupiter's moon Europa or Saturn's moon Enceladus. These hidden oceans could be hundreds of kilometers deep, potentially harboring life in their dark depths. There's another complication. Like Proxima b, the TRAPPIST-1 planets are almost certainly tidally locked. Each planet keeps one face eternally toward the star and one face in perpetual darkness. This creates extreme temperature differences, potentially a scorching day side and a frozen night side. But again, a thick atmosphere could save the day. Powerful winds might redistribute heat from the day side to the night side, creating a terminator zone, the twilight region between eternal day and eternal night, where conditions might be most temperate. Life, if it exists, might thrive in this twilight band. And then there's the star itself. Like all red dwarfs, TRAPPIST-1 is magnetically active, unleashing powerful stellar flares that bathe the planets in ultraviolet and X-ray radiation. Early in the system's history, billions of years ago, these flares would have been even more intense, potentially stripping away planetary atmospheres before life could even begin. Unless the planets have strong magnetic fields, like Earth's, which deflect harmful radiation, or unless they formed with so much water that even after losing large amounts to flares, enough remained to create habitable conditions. These are the questions that keep astronomers up at night, pondering the possibilities. For years after the TRAPPIST-1 system's discovery, the biggest question remained: do these planets have atmospheres? And if so, what are they made of? The key to answering this question is transmission spectroscopy. When a planet transits across its star, some of the starlight passes through the planet's atmosphere, if it has one. Different molecules in the atmosphere absorb specific wavelengths of light, creating a unique chemical fingerprint. By analyzing this fingerprint, we can determine what the atmosphere is made of. Previous observations with the Hubble Space Telescope and Spitzer had tried to detect atmospheres around the TRAPPIST-1 planets, with frustratingly inconclusive results. The planets are small, the star is dim, and the atmospheric signals, if they exist, are incredibly faint. What was needed was a revolutionary new telescope. Enter the James Webb Space Telescope, JWST, launched on December 25, 2021, and fully operational by mid-2022. With its massive 6.5-meter mirror and unprecedented infrared sensitivity, JWST is the most powerful space telescope ever built, and the TRAPPIST-1 system was among its highest priority targets. In March 2023, astronomers announced the first JWST results for TRAPPIST-1b, the innermost planet. The verdict? The planet likely has little to no atmosphere. The observations showed that the planet's dayside temperature is around 500 Kelvin, hot enough to vaporize most molecules and consistent with a bare rock directly exposed to the star's radiation. It was disappointing, but not surprising. TRAPPIST-1b orbits so close to its star that any atmosphere would have been blasted away by stellar radiation long ago. But the inner planets were never the most promising candidates for habitability. The real test would come with the planets farther out. In June 2023, results came in for TRAPPIST-1c. Again, the evidence suggested little to no thick atmosphere. The planet appears to be a bare rock, or at best has an extremely thin atmosphere rich in carbon dioxide. Another disappointment, but TRAPPIST-1c is also outside the habitable zone, so hopes weren't high. The crucial observations are those of TRAPPIST-1e, F, and G, the planets in the habitable zone. As of early 2024, JWST has observed these worlds, and teams of astronomers are carefully analyzing the data. Early indications are mixed. Some observations suggest the planets may lack thick atmospheres, while others leave the question open. Detecting atmospheres around these planets is extraordinarily difficult. The signals are faint, and even JWST is pushing the limits of what's possible. Multiple observations are needed to build up enough data to reach definitive conclusions. And even if an atmosphere is detected, determining its composition, whether it contains water vapor, oxygen, methane, or other biosignatures, will require even more observations. What we're witnessing is science at its frontiers, careful, painstaking, frustrating, and ultimately rewarding work. Each observation rules out some possibilities and constrains others. Each new piece of data brings us closer to understanding these distant worlds. The absence of thick atmospheres on the inner planets doesn't mean the habitable zone planets are airless. They're farther from the star, cooler, and may have retained their atmospheres despite stellar flares. Or they might have lost their original atmospheres, but developed secondary atmospheres through volcanic outgassing, similar to how Earth's atmosphere evolved over billions of years. The truth is, we don't yet know what the TRAPPIST-1 planets are like. They might be barren, airless rocks. They might have thin atmospheres of carbon dioxide. Or they might surprise us, harboring water vapor, oxygen, perhaps even signs of life. The answer is waiting in the data, and with each passing observation, we edge closer to the truth. Why is studying the TRAPPIST-1 system so challenging? Why can't we just point our telescopes at these planets and see what they're like? The problem is distance and scale. The TRAPPIST-1 system is 40 light-years away, about 380 trillion kilometers. At that distance, even with our most powerful telescopes, the planets don't appear as disks with features we can map. They're simply points of light, and even that point of light is overwhelmed by the glare of their star. To put it in perspective, TRAPPIST-1e reflects less than 1/10,000,000th of its star's light. Trying to see the planet next to its star is like trying to see a firefly next to a searchlight from 1,000 miles away. It's not impossible, but it requires extraordinary technology and clever techniques. Then there's the star itself. TRAPPIST-1 is magnetically active and variable. It has star spots, cooler regions on its surface, that come and go, changing the star's brightness. It has flares that can temporarily increase its brightness by 10% or more. All this variability makes it difficult to measure the tiny signals from planetary transits and atmospheres. Observing time on JWST is precious. Hundreds of teams compete for every hour of telescope time. To properly characterize a single TRAPPIST-1 planet's atmosphere might require 50 hours or more of observations. Observations that must be repeated to confirm results. With 7 planets in the system, that's hundreds of hours of the world's most advanced telescope, all dedicated to one star system. But JWST isn't working alone. Ground-based telescopes continue to monitor the system, measuring the planet's masses more precisely through gravitational interactions. The Hubble Space Telescope contributes observations in wavelengths JWST can't access, and future missions are being planned. NASA and international partners are developing next-generation space telescopes specifically designed to image and characterize potentially habitable exoplanets. Concepts like LUVOIR, the Large UV/Optical Infrared Surveyor, and HabEx, the Habitable Exoplanet Observatory, would have the power to directly image TRAPPIST-1 planets, separating their light from their star's glare. With direct imaging, we wouldn't just detect atmospheres. We could map them. We could watch weather patterns evolve. We could search for seasonal changes that might indicate vegetation or other biological processes. We could look for light reflected from oceans or the spectral signatures of chlorophyll or other biological pigments. These future missions are still in the planning stages, likely decades away from launch. But the groundwork is being laid now. Every observation of TRAPPIST-1 with JWST teaches us what we'll need to look for when more powerful telescopes come online. We're learning how to read the atmospheres of distant worlds, preparing for the day when we'll have the tools to truly understand what these planets are like. The question that captivates everyone, scientists and dreamers alike, is simple. Could there be life in the TRAPPIST-1 system? Life as we know it requires 3 basic ingredients: liquid water, organic molecules, the carbon-based building blocks of life, and an energy source. The TRAPPIST One system could potentially provide all three. If TRAPPIST-1 F, or G have atmospheres and liquid water on their surfaces, or subsurface oceans beneath ice, that's two ingredients checked off. Organic molecules are common throughout the universe, found even in interstellar space and comets. So that's likely not a limiting factor. Energy is more complicated. On Earth, most life ultimately depends on photosynthesis, organisms that capture energy from sunlight. But TRAPPIST-1's light is primarily infrared, quite different from our sun's visible light. Could photosynthesis work under a red dwarf's dim, reddish light? The answer appears to be yes. Laboratory studies have shown that Earth plants can photosynthesize using infrared light, though less efficiently than with visible light. And life on TRAPPIST-1 planets would have had billions of years to adapt to their star-specific light spectrum. Evolution is remarkably creative. Life might find ways to harvest energy that we haven't even imagined. And there are alternatives to photosynthesis. On Earth, life thrives around hydrothermal vents at the bottom of the ocean, in complete darkness, using chemical energy from volcanic activity. TRAPPIST-1 planets might have similar energy sources, particularly if they're geologically active due to tidal heating from gravitational interactions with their neighboring planets. But there are serious obstacles. The stellar flares from TRAPPIST-1 deliver powerful doses of ultraviolet radiation, harmful to most life forms. On Earth, our ozone layer protects us from UV radiation. TRAPPIST-1 planets would need similar protection, or life would need to shelter underground, underwater, or in caves. Yet even this might not be insurmountable. Some Earth organisms thrive in high-radiation environments. Life might evolve protective pigments, DNA repair mechanisms, or simply live beneath the surface or underwater where radiation can't reach. The question isn't whether the challenges are severe. They are. The question is whether life could adapt and overcome them. The tidal locking presents both challenges and opportunities. A permanent dayside and nightside create extreme environments, but the Terminator Zone, the band of perpetual twilight, might offer stable, moderate conditions. And if there's a global ocean, even beneath ice, the entire volume of water could be habitable, shielded from radiation and temperature extremes. If life exists on TRAPPIST-1 planets, could we detect it? We'd look for biosignatures, gases in the atmosphere that are produced by life and wouldn't persist without it. On Earth, oxygen is a powerful biosignature, produced by photosynthetic organisms and reacting away quickly unless replenished. The combination of oxygen with methane is even more compelling. These gases react with each other, so their simultaneous presence suggests active biological processes. JWST and future telescopes will search for these biosignatures. It's painstaking work, requiring hundreds of hours of observations to detect the faint chemical fingerprints in planetary atmospheres. But if we find them, if we detect oxygen or methane or other biosignature combinations, it would be the discovery of the millennium, proof that we are not alone. The TRAPPIST-1 system is more than just 7 planets around one star. It's a window into understanding planetary systems throughout the galaxy. Red dwarf stars like TRAPPIST-1 are the most common stars in the galaxy, making up about 75% of all stars. If compact multi-planet systems like TRAPPIST-1 are common around red dwarfs, and evidence suggests they might be, then planetary systems with multiple potentially habitable worlds could outnumber systems like our own solar system. TRAPPIST-1 isn't alone. We've discovered other red dwarf systems with multiple planets in habitable zones. Proxima Centauri, our nearest neighbor, has at least one potentially habitable planet and possibly more. LHS 1140, 49 light-years away, has a planet that might be a water world. TOI 700, 100 light-years distant, has multiple Earth-sized planets in its habitable zone. When we extrapolate from these discoveries, the implications are staggering. There might be hundreds of billions of potentially habitable planets orbiting red dwarf stars in our galaxy alone. Not all of them will actually be habitable. Many will lack atmospheres, or be too hot, or too cold, or face other obstacles. But even if only a small fraction are truly habitable, that still means billions of worlds where life might exist. Studying TRAPPIST-1 teaches us about how planetary systems form and evolve. Why do some systems have many planets while others have few? Why are some planets rocky while others are gaseous? How do planets interact gravitationally over billions of years? Every answer raises new questions, deepening our understanding of the cosmic processes that create worlds. The TRAPPIST-1 system likely formed differently than our solar system. Its compact configuration and orbital resonances suggest the planets formed farther from their star and migrated inward, sculpted by gravitational interactions with the disk of gas and dust that once surrounded TRAPPIST-1. This migration process might be common, helping explain why we find planets in unexpected places around many stars. Why does the TRAPPIST-1 system capture our imagination so powerfully? What is it about these 7 distant worlds that speaks to something deep within us? Perhaps it's because TRAPPIST-1 represents hope. Hope that habitable worlds are common, that we're not alone, that the universe is filled with possibilities we're only beginning to discover. For all of human history, we could only wonder about other worlds. Now, for the first time, we have the tools to actually study them, to learn what they're like, perhaps even to detect signs of life. Young people today are growing up in an era of unprecedented discovery. They'll likely live to see definitive answers about TRAPPIST-1's atmospheres, about whether these planets have water, perhaps even about whether they harbor life. They may witness humanity's first confirmed detection of life beyond Earth, a moment that will define their generation, just as the moon landing defined an earlier one. The TRAPPIST-1 system has inspired artists, musicians, writers, and dreamers. There's something poetic about 7 worlds orbiting in harmony, something that speaks to our sense of cosmic beauty and order. It reminds us that the universe is not just vast and empty, but filled with intricate systems of stunning complexity and elegance. The study of TRAPPIST-1 is also a testament to human cooperation. Astronomers from Belgium, the United States, the United Kingdom, and dozens of other countries have collaborated to observe and understand this system. The telescopes used, TRAPPIST, Spitzer, JWST, Hubble, ground-based facilities around the world, represent the combined efforts of thousands of scientists, engineers, and visionaries. And perhaps most profoundly, TRAPPIST-1 forces us to confront deep philosophical questions. If we find life there, even simple microbial life, it would tell us that life is not unique to Earth, but the processes that created life here have happened elsewhere. And if life arose independently in 2 star systems just 40 light-years apart, what does that say about the prevalence of life in a galaxy spanning 100,000 light-years? 40 light-years away, 7 worlds orbit a dim red star. They're locked in a gravitational dance that has persisted for billions of years. Some may be barren rocks, some may be frozen wastelands, but some, just perhaps, might be ocean worlds with atmospheres, with liquid water, with life. We're watching. We're listening. We're analyzing every photon of light that makes the 40 light-year journey from TRAPPIST-1 to our telescopes. Each observation brings us closer to understanding these alien worlds. Each new piece of data constrains the possibilities and sharpens our questions. In the coming years and decades, more powerful telescopes will join the search. We'll map the atmospheres of the habitable zone planets. We'll search for biosignatures with ever greater sensitivity. And one day, Perhaps in our lifetimes, we may have our answer. The TRAPPIST-1 system has taught us that worlds are common, that planetary systems come in endless varieties, and that nature is far more creative than we ever imagined. Whether these 7 worlds harbor life or not, they've already changed us. They've shown us that the universe is not barren, but filled with worlds waiting to be understood. So the next time you look up at the night sky, remember, in the constellation Aquarius, too faint to see with the naked eye, but visible to our greatest telescopes, lies a star system of 7 worlds. They're out there right now, orbiting in cosmic harmony, keeping their secrets, and we're determined to uncover them. The TRAPPIST-1 system, 7 worlds, 3 in the habitable zone, countless questions. The search continues. Next, let's begin unraveling Osiris, the enigmatic exoplanet HD 209458b. The TRAPPIST-1 system showed us nature's abundance, 7 Earth-sized worlds packed into a space smaller than Mercury's orbit. We study these planets using the transit method, watching them pass in front of their star, analyzing the starlight that filters through their atmospheres. But where did this technique come from? How do we learn to read the atmospheres of distant worlds by watching them cross their stars? The answer takes us back to 1999 to a discovery that changed everything. The first exoplanet ever observed transiting its star. Welcome to HD 209458b, nicknamed Osiris after the Egyptian god. This wasn't just another exoplanet. It was the Rosetta Stone that taught us how to decipher the secrets of alien atmospheres. This is the story of the planet that pioneered a revolution. Imagine a world so close to its star that its atmosphere is literally boiling away into space. A gas giant where the temperature reaches 1,000 degrees Celsius, where metals vaporize and winds scream at supersonic speeds. A planet so extraordinary that it earned the name of an ancient god, Osiris. This is HD 209458b, and it made history, not once, but multiple times. It was the first exoplanet ever observed crossing in front of its star. The first exoplanet with a measured atmosphere. The first to show us that planets can lose their atmospheres to space. And the first to teach us techniques we now use to study thousands of other worlds. Before Osiris, exoplanets were invisible, detected only through their gravitational effects on their stars. After Osiris, we could see them, study them, understand them. This is the story of the planet that opened our eyes. Our story begins in 1999, just 4 years after the discovery of 51 Pegasi b proved that exoplanets exist. Astronomers had found dozens of exoplanets using the radial velocity method, measuring the wobble of stars caused by orbiting planets. But they had never actually seen an exoplanet. They had only inferred their existence from their gravitational effects. Among these discoveries was HD 209458b, found earlier in 1999 by astronomers Geoffrey Marcy and Paul Butler using radial velocity observations. It was a hot Jupiter, a gas giant orbiting incredibly close to its sun-like star, completing an orbit every 3.5 days. But what made this planet special wasn't yet apparent. That same year, 2 teams of astronomers had the same brilliant idea. If HD 209458b's orbit was aligned just right, if we were viewing the system edge-on, then the planet should pass directly in front of its star from our perspective. And if that happened, the planet would block a tiny fraction of the star's light, causing immeasurable dimming that we could detect. David Charbonneau, then a graduate student at Harvard, and Greg Henry at Tennessee State University led one team. Another team, led by Timothy Brown, worked independently. Both groups trained their telescopes on HD 209458 in September 1999, hoping to catch the planet in the act of transiting. And there it was. For approximately 3 hours, the star's brightness dropped by 1.7%, exactly as predicted if a Jupiter-sized planet was passing in front of it. Both teams detected the transit independently, confirming each other's results. It was November 1999, and exoplanet science had just entered a new era. The discovery made headlines around the world. For the first time in human history, we had directly observed an exoplanet crossing its star. This wasn't just inferring a planet's existence. This was watching it happen in real time. And the implications were staggering. The transit told us the planet's size. By measuring how much light it blocked, we knew its radius precisely. Combined with the radial velocity data giving us its mass, we could calculate its density, telling us what the planet was made of. But most importantly, during the transit, starlight passed through the planet's atmosphere on its way to us. And hidden in that starlight was information about what gases existed in that alien atmosphere. Before HD 209458b, we could find planets but barely characterize them. After HD 209458b, we had a tool to study their atmospheres, their temperatures, their compositions, to truly understand these distant worlds. It was like the difference between knowing a book exists and actually being able to read it. So what is HD 209458b? This world we call Osiris. Let's journey to this extreme planet and explore its hellish conditions. HD 209458b orbits a sun-like star located 160 light-years from Earth in the constellation Pegasus, the same constellation that hosts 51 Pegasi b, the first exoplanet discovered around a sun-like star. The star, HD 209458, is remarkably similar to our Sun, slightly more massive, slightly hotter, but fundamentally the same type of star. HD 209458b is classified as a hot Jupiter, a gas giant similar in mass to Jupiter, but with a crucial difference. While Jupiter orbits our Sun at a comfortable 778 million kilometers, taking nearly 12 years to complete one orbit, HD 209458b orbits at just 7 million kilometers from its star, 20 times closer than Mercury is to our Sun. Its orbital period? A blistering 3.5 Earth days. This proximity creates furnace-like conditions. The planet's day side, perpetually facing its star, reaches temperatures around 1,000 degrees Celsius, 1,800 degrees Fahrenheit. That's hot enough to melt silver, hot enough to vaporize many metals. The planet glows from its own heat, radiating in infrared wavelengths. Remarkably, HD 209458b is larger than Jupiter despite having slightly less mass. The intense stellar radiation heats the planet's atmosphere, causing it to puff up like a balloon. The planet's radius is about 1.4 times Jupiter's radius, giving it a surprisingly low density, less than half that of Jupiter. It's a bloated world, inflated by the relentless heat from its nearby star. Like most hot Jupiters, Osiris is tidally locked. One hemisphere eternally faces the star while the other faces away into darkness. But unlike rocky planets, gas giants have no surface for these hemispheres to look different. Instead, the entire atmosphere circulates, with supersonic winds carrying heat from the day side to the night side. Computer models suggest these winds reach speeds of several kilometers per second, thousands of miles per hour, driven by the extreme temperature difference between the star-facing and dark hemispheres. The atmosphere is in constant, violent motion, creating a dynamic, turbulent environment unlike anything in our solar system. The day side isn't uniformly hot, and the night side isn't uniformly cool. Instead, there's a complex pattern of temperature zones, with the hottest region offset from the substellar point, the location directly beneath the star, due to atmospheric circulation. These patterns create weather systems of unimaginable scale and intensity. The transit observations in 1999 proved we could detect exoplanets directly. But the real breakthrough came a few years later, when scientists figured out how to read the composition of Osiris's atmosphere. The first time this had ever been done for an exoplanet. In 2001, astronomers used the Hubble Space Telescope to observe HD 209458b during its transit. As the planet passed in front of its star, they collected spectra, spreading the star's light into its component wavelengths, like a prism splitting white light into a rainbow. Here's the key insight. As starlight passed through the planet's atmosphere on its way to us, different molecules in that atmosphere absorbed specific wavelengths of light. Each molecule has a unique absorption signature, a chemical fingerprint. By comparing the spectrum during the transit to the spectrum when the planet wasn't transiting, scientists could identify which wavelengths were absorbed by the planet's atmosphere, revealing what gases were present. The first detection was sodium, an alkali metal that should exist as vapor at the scorching temperatures of Osiris's atmosphere. It was announced in 2001 and confirmed in 2002. For the first time in human history, we had detected a specific chemical in the atmosphere of a planet orbiting another star. The technique worked. More discoveries followed rapidly. In 2003, hydrogen was detected in the planet's atmosphere, but not just present in the atmosphere. The hydrogen extended far beyond the planet itself, creating a huge cloud around the planet. This was evidence of something remarkable: atmospheric escape. At the extreme temperatures of Osiris's atmosphere, hydrogen atoms gain enough energy to escape the planet's gravity entirely. The planet is literally evaporating, losing atmosphere to space at an estimated rate of 10,000 tons per second. Over time, Osiris could lose a significant fraction of its mass, perhaps already has lost substantial mass over its lifetime. Even more surprising, heavier elements like carbon and oxygen were also detected in the escaping atmosphere. These elements, far heavier than hydrogen, shouldn't be able to escape, except that the rapidly escaping hydrogen drags them along, like a river carrying debris. It's a process called hydrodynamic escape, and HD 209458b provided the first direct evidence that this happens on hot Jupiters. In 2007, water vapor was detected in Osiris's atmosphere using the Spitzer Space Telescope, the first unambiguous detection of water on an exoplanet. This was followed by methane and carbon dioxide. Suddenly, we weren't just detecting elements, but complex molecules, building a detailed chemical picture of this alien world. Today, we know Osiris's atmosphere contains hydrogen, helium, sodium, carbon, oxygen, water vapor, carbon monoxide, carbon dioxide, and methane. We've measured temperature profiles showing how temperature changes with altitude. We've detected winds and circulation patterns. We've mapped the distribution of molecules across the planet. HD 209458b became the prototype, the standard against which all other hot Jupiter atmospheres are compared. Every new technique, every new instrument was first tested on Osiris. It remains one of the most studied exoplanets, with hundreds of observations from dozens of telescopes over more than 2 decades. HD 209458b didn't just give us data about one planet. It gave us the tools to study all planets. Let's explore the techniques pioneered on Osiris that are now used throughout exoplanet science. The transit method seems simple. Watch for a star to dim when a planet passes in front of it. But extracting useful information requires extraordinary precision. The dimming caused by HD 209458b is just 1.7%, and that's for a Jupiter-sized planet. An Earth-sized planet causes a dimming of just 0.01%, requiring measurements accurate to 1 part in 10,000. The success with HD 209458b proved the transit method worked, leading directly to NASA's Kepler Space Telescope, launched in 2009. Kepler monitored 150,000 stars simultaneously, searching for transits, and discovered thousands of exoplanets. Its successor, TESS, the Transiting Exoplanets Survey, continues this work today, having discovered thousands more planets. Transmission spectroscopy, analyzing starlight that passes through a planet's atmosphere during transit, was first demonstrated successfully with HD 209458b. Today, it's the primary method we use to study exoplanet atmospheres. We've used it on dozens of planets, from hot Jupiters to super-Earths to potentially habitable worlds. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has revolutionized transmission spectroscopy. JWST observations can detect far more molecules, measure temperatures more precisely, and study smaller planets than ever before, all building on techniques pioneered with Osiris. HD 209458b also pioneered the secondary eclipse method. When a planet passes behind its star from our perspective, the combined light of star and planet drops slightly as the planet disappears. By measuring this drop, we can determine how much light the planet itself emits and reflects, telling us about the planet's temperature, albedo, and atmospheric properties on the day side. By observing the entire orbit, watching how the combined light changes as the planet goes from being fully illuminated to being backlit, we can create phase curves that map the temperature distribution across the planet. This technique, first demonstrated with HD 209458b, reveals atmospheric circulation patterns and tells us how efficiently planets transport heat from day to night sides. High-resolution spectroscopy, which uses Earth's motion to separate planetary signal from stellar signals through Doppler shifting, has also been extensively used on HD 209458b. This technique can detect extremely faint atmospheric signals and has revealed wind speeds, chemical gradients, and atmospheric dynamics. What makes HD 209458b particularly valuable is that it's bright enough and transits frequently enough that many different telescopes can observe it using many different techniques. It's become the standard candle of exoplanet science, a benchmark against which new instruments and methods are tested. The discoveries from HD 209458b rippled through planetary science, reshaping our understanding of how planets form, evolve, and behave. Let's explore the profound impact Osiris has had on our knowledge of exoplanetary systems. HD 209458b, like 51 Pegasi b before it, posed a fundamental question. How did a gas giant end up so close to its star? Gas giants should form beyond the frost line, where it's cold enough for ice to condense. The answer, planetary migration, was already suspected, but Osiris provided crucial evidence. We now understand that young planets interact with the disk of gas and dust surrounding their star. These interactions cause planets to spiral inward or outward, migrating from where they formed. HD 209458b likely formed much farther from its star, perhaps where Jupiter is in our solar system, and then migrated inward over millions of years, finally settling into its current scorching orbit. The atmospheric escape observed on HD 209458b revealed that planetary atmospheres aren't static. They evolve over time. Planets can lose substantial mass, especially early in their lives when their stars are more active and luminous. This process helps explain the diversity of exoplanets we observe. The Neptune Desert, a relative lack of Neptune-sized planets orbiting very close to their stars, might be explained by atmospheric escape. These planets may have once been larger, losing their atmospheres over time and shrinking to become the hot super-Earths we observe today. HD 209458b showed us the process in action. Observations of HD HD-209-458b's atmosphere led to sophisticated computer models of atmospheric circulation on hot Jupiters. These models predict fast winds, complex temperature patterns, and chemical gradients, predictions that have been confirmed by observations of Osiris and other hot Jupiters. We now understand the basic atmospheric dynamics of these extreme worlds. The molecular detections in Osiris's atmosphere, water, methane, carbon dioxide, carbon monoxide, taught us that hot Jupiter atmospheres are chemically rich and complex. The relative abundances of these molecules tell us about the planet's formation history, particularly how much solid material it incorporated compared to gas. The carbon-to-oxygen ratio in a planet's atmosphere is particularly revealing. A high care-of ratio suggests the planet formed farther from its star and migrated inward, while a low care-of ratio suggests formation closer to the star. HD-209-458b's atmospheric chemistry helped establish this connection, giving us a tool to trace the migration histories of exoplanets. HD-209-458b's surprisingly large radius, inflated by stellar heating, revealed that hot Jupiters come in different flavors. Some are dense, compact worlds. Others, like Osiris, are bloated and puffy. Understanding why some planets inflate more than others remains an active area of research, with theories involving atmospheric circulation, core heating, and tidal interactions. Perhaps most importantly, HD-209-458b established the field of comparative exoplanetology, the systematic study and comparison of different exoplanets to understand the underlying physical principles. Just as comparative planetology in our solar system taught us about planetary processes, comparing exoplanets teaches us about the incredible diversity of worlds that exist. More than 2 decades after its discovery, HD-209-458b remains at the forefront of exoplanet research. Let's reflect on the remarkable legacy of this pioneering world. When HD-209-458b was discovered in 1999, we knew of fewer than 30 exoplanets. Today, we know of more than 5,000, with thousands more candidates awaiting confirmation. The transit method pioneered with Osiris has found the vast majority of these planets. When Osiris became the first exoplanet with a studied atmosphere in the early 2000s, it stood alone. Today, we've characterized the atmospheres of more than 100 exoplanets, from hot Jupiters to mini-Neptunes to super-Earths, all using techniques first demonstrated on HD-209-458b. The transit observations of HD-209-458b taught us how to measure planetary sizes precisely, revealing an astonishing diversity of worlds. We found planets smaller than Mercury and planets larger than Jupiter, rocky planets, ice giants, gas giants, water worlds, lava planets, a cosmic menagerie of worlds that defies easy categorization. Even today, HD-209-458b remains heavily observed. The James Webb Space Telescope has observed it multiple times, detecting additional molecules and measuring atmospheric properties with unprecedented precision. Ground-based telescopes continue to monitor it, studying its variability and long-term evolution. Future missions will continue studying HD-209-458b. ESA's aerial mission, planned for the 2030s, will survey the atmospheres of hundreds of exoplanets, but will inevitably return to Osiris, the planet that started it all, for detailed comparative studies. Over 500 scientific papers have been published about HD-209-458b, more than any other exoplanet except possibly 51 Pegasi b. Each observation, each analysis, each model contributes to our understanding not just of this one world, but of exoplanets in general. HD 209458b has also become an icon in science education. It appears in textbooks, documentaries, planetarium shows. Students learning about exoplanets study Osiris as the example that demonstrates fundamental concepts. It's the planet that taught us, scientists and public alike, how to think about alien worlds. HD 209458b showed us how to study exoplanet atmospheres, but the ultimate goal was always to search for life. How do the lessons from Osiris apply to that greatest of all questions? HD 209458b itself is utterly inhospitable to life as we know it. It has no surface, scorching temperatures, and intense radiation. But the techniques developed to study Osiris, transit observations, transmission spectroscopy, atmospheric characterization, are now being applied to potentially habitable worlds. When we observe TRAPPIST-1 searching for water vapor and oxygen, we're using methods pioneered on HD 209458b. When we study Proxima Centauri, be looking for atmospheric signatures, we're applying lessons learned from Osiris. The path from hot Jupiters to habitable worlds is direct. The next frontier is biosignature detection, identifying chemical combinations in exoplanet atmospheres that indicate the presence of life. Oxygen and methane together, phosphine or dimethyl sulfide. These searches require the same techniques used on HD 209458b, just pushed to ever greater precision. The next generation of telescopes, both ground-based, extremely large telescopes and future space missions, will have the sensitivity to detect biosignatures on potentially habitable planets. They'll study smaller planets, cooler planets, planets in the habitable zones of sun-like stars. And they'll build on the foundation laid by HD 209458b. Think about the journey. In 1999, we observed our first transiting exoplanet. In the early 2000s, we detected our first exoplanet atmosphere. In the 2010s, we surveyed thousands of planets. In the 2020s, we're characterizing atmospheres of potentially habitable worlds. And in the 2030s and beyond, we might detect life itself. None of this would have been possible without HD 209458b. It was the proof of concept, the testbed, the pioneer that showed us the way forward. Every exoplanet observation, every atmospheric detection, every biosignature search stands on the shoulders of Osiris. 160 light-years away, in the constellation Pegasi, a gas giant orbits its star every 3.5 days. Its atmosphere boils away into space. Winds race at supersonic speeds. The dayside glows at 1,000 degrees Celsius. It's a world we could never live on, a planet that seems more alien than anything in our solar system. Yet this world, HD 209458b, Osiris, changed everything. It taught us how to see exoplanets, how to study their atmospheres, how to understand their compositions, their temperatures, their winds, their chemistry. From that first transit observation in 1999 has grown an entire field of science. We've studied hundreds of atmospheres, discovered thousands of planets, begun the search for life beyond Earth. And at the foundation of it all is Osiris, the planet that showed us the way. Today, over 2 decades later, we're still observing HD 209458b, still learning from it, still using it to test new techniques that will apply to other worlds. It remains a beacon in exoplanet science, the standard, the exemplar, the pioneer. The next time you look up at the constellation Pegasi in the night sky, remember, among those stars shines HD 209458, and orbiting that star is a world that taught humanity how to read the atmospheres of alien planets. Osiris, the first of its kind, and forever the planet that opened our eyes to distant worlds. The discoveries continue. If you thought that last one was cool, let's get into exploring one of my personal favorites, Kepler 186f, Earth's twin in stars. HD 209458b, Osiris, taught us how to find planets through transits and study their atmospheres through spectroscopy. The Kepler Space Telescope took these lessons and scaled them up, monitoring 150,000 stars simultaneously, searching for Earth's twin among the stars. For 4 years, Kepler watched the skies, detecting thousands of planets. Hot Jupiters like Osiris, mini Neptunes, super-Earths, worlds of every imaginable size and type. But there was one type of planet that had eluded us, the holy grail of exoplanet science, an Earth-sized planet orbiting in the habitable zone of its star. Until April 17, 2014, when astronomers announced a discovery that made headlines around the world. 500 light-years away, orbiting a dim red dwarf star, they'd found it, Kepler 186f, the first Earth-sized planet confirmed in the habitable zone. Welcome to Earth's distant cousin. Imagine a world about the size of Earth, orbiting at just the right distance from its star for liquid water to exist on its surface. A world where the conditions might be right for life. A world that, for the first time, truly resembles our own. This is Kepler 186f, not quite Earth's twin, but perhaps its cousin. Discovered in 2014, it was the first confirmed planet of Earth size found in the habitable zone of another star. After centuries of wondering if worlds like ours exist beyond our solar system, we finally had our answer. Yes, they do. The discovery came from NASA's Kepler Space Telescope, a mission specifically designed to answer one question: how common are Earth-like planets in our galaxy? Kepler 186f wasn't just another exoplanet. It was proof that planets the size of Earth, orbiting in habitable zones, actually exist. It was a milestone that changed how we think about our place in the universe. Our story begins in March 2009, when NASA launched the Kepler Space Telescope into orbit around the Sun, named after Johannes Kepler, the 17th-century astronomer who discovered the laws of planetary motion. The spacecraft carried a mission of profound importance: to determine how common Earth-sized planets are in our galaxy. Kepler monitored a single patch of sky in the constellation Cygnus, continuously observing 150,000 stars for more than 4 years. The spacecraft used the transit method, watching for the slight dimming when a planet passes in front of its star, a technique pioneered with HD 209458b. But Kepler operated at a scale never before attempted. Detecting an Earth-sized planet requires extraordinary precision. When Earth passes in front of the Sun from a distant perspective, it blocks just 0.008% of the Sun's light, less than 1 part in 10,000. Kepler had to measure stellar brightness to within a few parts per million, detecting changes far smaller than the human eye could perceive. Over its mission lifetime, Kepler detected thousands of planetary candidates. Most were large, Jupiter-sized or Neptune-sized planets that block more light and are easier to detect. But the mission was designed to find the small planets, the Earth-sized worlds that might harbor life. 500 light-years away, in the constellation Cygnus, lies a star cataloged as KIC 8120608, later renamed Kepler 186. It's an unremarkable star. Small, cool, dim. You need a telescope to see it at all. But something about this star caught Kepler's attention. The star dimmed periodically, not once, but multiple times in distinct patterns suggesting multiple planets. By 2014, astronomers had confirmed 5 planets orbiting Kepler 186, all detected through their transits. The inner 4 were larger than Earth, orbiting too close to their star to be habitable. But the 5th planet, the outermost one, was different. It caused a dimming of just 0.02%, lasting about 4.5 hours. From this faint signal, astronomers could calculate the planet's size, about 1.1 times Earth's radius, making it the most Earth-sized planet yet discovered in a habitable zone. On April 17, 2014, NASA held a press conference to announce the discovery. The news made front pages worldwide. After decades of searching, we had finally found a truly Earth-sized planet orbiting in the habitable zone of its star. Kepler 186f was designated, and a new era in exoplanets science began. The discovery was more than just one planet. It was validation that the Kepler mission strategy worked. If Earth-sized planets in habitable zones exist around one random star, they might exist around millions, even billions of stars. Suddenly, Earth-like worlds seem not just possible but common. To understand Kepler 186f, we must first understand its cosmic home, the Kepler 186 system, a miniature solar system unlike our own, yet tantalizingly familiar. Kepler 186 lies approximately 500 light-years from Earth in the constellation Cygnus, the Swan. That's about 10 times farther than Proxima Centauri, our nearest stellar neighbor, but still within our cosmic neighborhood. Light from Kepler 186 left its star around the year 1524, during the Renaissance on Earth, and is just now reaching our telescopes. Kepler 186 is what astronomers call an M-dwarf or red dwarf star, the most common type of star in our galaxy. It has just 47% of the Sun's mass and only 4% of the Sun's luminosity. It's smaller than our Sun, cooler, dimmer, and redder. If you could see Kepler 186 in Earth's night sky, it would appear as a faint reddish point of light, magnitude 14.6, far too dim for the naked eye. The star's surface temperature is about 3,800 Kelvin, relatively cool compared to the Sun's 5,800 Kelvin. This coolness means most of its light is emitted in the red and infrared portions of the spectrum. Standing on a planet orbiting Kepler 186, the star would appear salmon-colored or deep orange-red, not the yellow-white of our Sun. The Kepler 186 system contains 5 known planets, all discovered by the Kepler mission through transit observations. Let me introduce them from innermost to outermost. Kepler 186b is the innermost planet, about 1.07 times Earth's radius. It orbits extremely close to its star, just 5.9 million kilometers or 0.04 AU, completing one orbit every 3.9 Earth days. At this distance, the planet is scorching hot, with estimated surface temperatures around 620 Kelvin or 350 degrees Celsius. Far too hot for life as we know it. Kepler 186c orbits at 9.4 million kilometers or 0.06 AU, with a period of 7.3 days. At 1.25 Earth radii, it's slightly larger than Earth. Surface temperatures are still extreme, around 500 Kelvin. Again, uninhabitable. Kepler 186d at 1.4 Earth radii is the largest of the 5 planets. It orbits at 0.08 AU with a period of 13.3 days. Estimated temperature, 430 Kelvin, still too hot for liquid water. Kepler 186e is 1.27 Earth radii and orbits at 0.11 AU with a 22.4-day period. Temperatures drop to around 370 Kelvin, hot, but approaching the range where, with the right atmospheric conditions, water might persist. And then, at 0.43 AU, about 64 million kilometers from its star, we find Kepler 186f, the outermost of the 5 planets, and the only one in the habitable zone. The planets of Kepler 186 are packed tightly together, with the entire system fitting within the orbit of Mercury in our solar system. The inner 4 planets are spaced in what appears to be a non-resonant configuration. Their orbital periods don't form simple ratios, though more observations are needed to confirm the exact dynamics. The Kepler 186 system reminds us of other compact systems we've discovered, like TRAPPIST-1 with its 7 worlds. These tightly packed planetary systems seem to be common around red dwarf stars, perhaps because planets form closer to dim stars to receive enough warmth. So what is Kepler 186f? What do we know about this distant world, and what mysteries remain unsolved? Kepler 186f is approximately 1.17 times Earth's radius, just slightly larger than our home planet. This makes it definitively Earth-sized, not a super-Earth. It's the closest we've come to finding a true Earth analog in terms of size among planets in habitable zones. The planet's mass is uncertain because the transit method only tells us size, not mass. However, based on its radius and assuming various compositions, astronomers estimate Kepler 186f has between 1.4 and 2.9 Earth masses. The exact value depends on whether the planet is rocky like Earth, has a larger iron core, or contains significant amounts of water. If Kepler 186f is primarily rocky with an iron core like Earth, its mass would be around 1.4 to 1.7 Earth masses. If it's more water-rich, an ocean world, it could be more massive while maintaining the same radius. Without radial velocity measurements to determine mass directly, we can only estimate based on composition models. Kepler 186f orbits at approximately 0.43 AU, about 64 million kilometers from its star. To put this in perspective, that's closer than Venus is to our Sun. But remember, Kepler 186 is much dimmer than our Sun, producing only 4% of the Sun's energy output. At this distance, Kepler 186f receives about 32% of the energy flux that Earth receives from the Sun. This places Kepler 186f near the outer edge of the habitable zone, the region where temperatures could allow liquid water on the surface. If the planet has no atmosphere, surface temperatures would be well below freezing, around 188 Kelvin or minus 85 degrees Celsius. Far too cold for life. But if Kepler 186f has an atmosphere with greenhouse gases, carbon dioxide, water vapor, methane, it could trap enough heat to warm the surface above the freezing point of water. With a thick enough atmosphere, perhaps similar to Earth's or even somewhat thicker, surface temperatures could be tempered enough for liquid water oceans. Kepler 186f completes one orbit every 129.9 Earth days, about 4 Earth months. That's its year. But what about its day? How fast does the planet rotate? We don't know for certain. At 0.43 AU from a red dwarf star, Kepler 186f might be tidally locked, with one side permanently facing the star and the other in perpetual darkness, just like the moon is tidally locked to Earth. However, Kepler 186f orbits farther from its star than many red dwarf planets, and tidal locking isn't certain. The planet might rotate slowly, experiencing long days and nights, or it might have retained a faster rotation. We don't know the planet's axial tilt, so we can't say whether it experiences seasons like Earth does. Without knowing its rotation period or axial tilt, much about its climate remains speculative. What would it be like to stand on Kepler 186f, assuming it has a solid surface? The star would appear about half the size of our Sun in Earth's sky, glowing a deep salmon-orange color. The illumination would be dimmer than Earth's daylight, perhaps like late afternoon or early morning light, but redder. If Kepler 186f has life, photosynthesis would operate under this redshifted light. Laboratory studies show that Earth plants can photosynthesize under red dwarf starlight, though less efficiently than under our Sun's light. Plants on Kepler 186f, if they exist, might appear black or very dark red to maximize light absorption, quite different from Earth's green foliage. The most fundamental question about Kepler 186f, the question that determines whether it's habitable or barren, is this: does it have an atmosphere? Atmospheres are crucial for life as we know it. They regulate temperature through the greenhouse effect. They shield the surface from harmful radiation. They enable liquid water to exist by providing pressure. Without an atmosphere, Kepler 186f would be a frozen, airless rock. With the right atmosphere, it could be a living world. Detecting an atmosphere around Kepler 186f is extraordinarily challenging. The planet is 500 light-years away, too distant for current transmission spectroscopy techniques to work effectively. The star is dim, and the planet's transit signal is faint. Even the James Webb Space Telescope would struggle to characterize Kepler 186f's atmosphere with current technology. Without direct observations, scientists rely on computer models to explore what kind of atmosphere Kepler 186f might have. These models test various scenarios: thin atmospheres, thick atmospheres, different compositions, different pressures. If Kepler 186f has an Earth-like atmosphere, 78% nitrogen, 21% oxygen, with traces of water vapor, carbon dioxide, and other gases, what would conditions be like? Models suggest the planet might be too cold for liquid water at the surface. Remember, it receives only 32% of Earth's solar flux. Even with Earth's greenhouse effect, the surface might remain frozen. A thicker atmosphere with more greenhouse gases could warm the planet. If Kepler 186f has several times Earth's atmosphere pressure and higher concentrations of carbon dioxide, similar to Venus but less extreme, the greenhouse effect might warm the surface enough for liquid water. The planet could have a climate range from Arctic-like to temperate. Some models suggest Kepler 186f might be a water world, a planet with a global ocean and no continents. If the planet formed with abundant water ices and has a thick hydrogen or water vapor atmosphere, it might resemble nothing in our solar system, an entirely ocean-covered world with extreme atmospheric pressures. Conversely, if Kepler 186f has too much atmospheric greenhouse warming, it could experience a runaway greenhouse effect like Venus, where temperatures soar and water boils away. The planet might appear habitable from a distance, but be a scorching hell up close. The most pessimistic scenario is that Kepler 186f has no substantial atmosphere at all. Red dwarf stars are magnetically active, producing powerful flares that bombard nearby planets with radiation. Over billions of years, this radiation could strip away atmospheres, especially if the planet lacks a strong magnetic field for protection. Earth's magnetic field, generated by our planet's molten iron core, shields us from the solar wind and helps protect our atmosphere. We don't know if Kepler 186f has a magnetic field. If it does, and if it's strong enough, the planet might have retained its atmosphere despite stellar flares. If not, the atmosphere might have been lost long ago. Red dwarf stars pose unique challenges for habitability. They're active for billions of years, producing flares that can temporarily increase their brightness by 10 to 100%. These flares deliver powerful doses of ultraviolet and X-ray radiation. Over time, this radiation can break apart atmospheric molecules and allow them to escape to space. However, Kepler 186f has an advantage. It orbits relatively far from its star compared to many red dwarf planets like TRAPPIST-1's worlds or Proxima b. This greater distance means less intense radiation, improving the chances that the planet retained its atmosphere. Kepler 186f represents more than just one planet. It represents a possibility, a proof of concept, a door that has opened revealing countless worlds beyond. Before Kepler 186f's discovery, We suspected Earth-sized planets in habitable zones might exist, but we had no confirmed examples. Kepler 186f proved they do exist. And if one exists, many more likely do as well. The Kepler mission ultimately discovered over 2,600 confirmed planets and thousands more candidates. Statistical analysis of Kepler's data suggests that approximately 20 to 50% of Sun-like stars have Earth-sized planets in their habitable zones. If we extend this to red dwarf stars, the most common stars in the galaxy, potentially habitable planets might number in the tens of billions in our galaxy alone. Since Kepler 186f, we've discovered many other Earth-sized planets in habitable zones. Kepler 442b, Kepler 452b, TRAPPIST-1e, and others. Each one is unique, with different orbital periods, different stellar hosts, different distances from Earth. Together, they paint a picture of a galaxy rich with potentially habitable worlds. But being in a habitable zone doesn't guarantee life. A planet must have the right atmosphere, liquid water, chemical building blocks for life, and an energy source. It must maintain stable conditions over geological timescales. It must avoid catastrophes like asteroid impacts or nearby supernovae. The habitable zone is necessary, but not sufficient. Kepler 186f orbits a red dwarf, and the habitability of red dwarf planets remains hotly debated among scientists. On one hand, red dwarfs live for trillions of years, plenty of time for life to evolve. They're the most common stars, meaning red dwarf planets outnumber all others. On the other hand, red dwarfs are magnetically active, produce intense flares, and their planets are often tidally locked. Some scientists argue that life around red dwarfs is unlikely due to these challenges. Others counter that life might adapt, sheltering underground during flares, photosynthesizing under red light, thriving in subsurface oceans shielded from radiation. The debate continues, and planets like Kepler 186f are the test cases. The ultimate test of Kepler 186f's habitability would be detecting biosignatures, chemical signs of life in its atmosphere. Oxygen combined with methane would be compelling evidence of biological processes. Other gases like dimethyl sulfide or phosphine might also indicate life. Unfortunately, detecting biosignatures on Kepler 186f is beyond our current capabilities. The planet is too distant, the star too dim, the signals too faint. Even the James Webb Space Telescope, our most powerful observatory, cannot characterize Kepler 186f's atmosphere in detail. Future telescopes, however, might succeed where current instruments cannot. Concepts like LUVOIR, the Large UV/Optical Infrared Surveyor, or HabEx, the Habitable Exoplanet Observatory, are being designed specifically to image and characterize Earth-sized planets in habitable zones. These missions, if built, could target Kepler 186f. More likely, future missions will focus on closer targets, planets like those in the TRAPPIST-1 system at 40 light-years, or Proxima b at just 4.24 light-years. These planets are more accessible for detailed study, but the techniques developed to study them will be inspired by what we learned from Kepler 186f. Kepler 186f's discovery was a triumph not just for one planet, but for an entire mission. NASA's Kepler Space Telescope, which revolutionized our understanding of planets in the universe. Launched in 2009, Kepler operated for 9 years, observing 530,000 stars and discovering 2,662 confirmed exoplanets, more than half of all known exoplanets. Its primary mission lasted 4 years until 2013, when reaction wheel failures threatened to end the mission. But ingenious engineers devised a new observing strategy, and Kepler continued as K2, discovering hundreds more planets until its retirement in 2018. Kepler found planets of every conceivable type. Hot Jupiters orbiting in days, super-Earths larger than our planet but smaller than Neptune, mini-Neptunes, circumbinary planets orbiting two stars, and yes, Earth-sized planets in habitable zones. The sheer diversity revealed by Kepler showed us that planetary systems come in endless varieties. Perhaps Kepler's greatest contribution wasn't any single planet, but the statistics. By surveying thousands of stars, Kepler told us how common different types of planets are. We learned that most stars have planets. That's super-Earths and mini-Neptunes. Sizes absent in our solar system are incredibly common. That compact multi-planet systems are normal, not exceptions. And crucially, Kepler told us that Earth-sized planets in habitable zones exist around a significant fraction of stars. Kepler 186f was the first confirmed example, but it wasn't alone. Statistical analysis suggests there could be tens of billions of potentially habitable Earth-sized worlds in our galaxy. In 2018, after exhausting its fuel supply, Kepler was decommissioned. It now drifts in a safe orbit around the Sun, a silent monument to one of humanity's greatest scientific achievements. But its legacy lives on in the data it collected and the planets it discovered. Kepler's successor, TESS, the Transiting Exoplanets Survey satellite, launched in 2018, continues the search for exoplanets, focusing on brighter, nearby stars that are easier to study in detail. Meanwhile, ground-based surveys and other space missions add to the growing census of exoplanets. Future missions like ESA's Plato, planned for the 2020s, will search for Earth-like planets around Sun-like stars. NASA's Nancy Grace Roman Space Telescope will use gravitational microlensing to find planets, including potentially habitable worlds. Each builds on Kepler's pioneering work. 500 light-years is an almost incomprehensible distance. Light, traveling at 300,000 kilometers per second, takes 500 years to make the journey from Kepler 186 to Earth. What would it take for humanity to visit this distant world? Our fastest spacecraft, Voyager 1, travels at about 17 kilometers per second relative to the Sun. At that speed, reaching Kepler 186f would take approximately 9 million years, far longer than our species has existed. Clearly, conventional propulsion won't work. Breakthrough Starshot, the light-sail concept aimed at reaching Proxima Centauri in 20 years by traveling at 20% light speed, would take 2,500 years to reach Kepler 186f. Even at a significant fraction of light speed, the journey would span multiple human generations. Science fiction has long imagined generation ships, massive spacecraft where multiple generations live and die during centuries-long journeys to distant stars. For a destination like Kepler 186f, a generation ship traveling at 1% light speed would take 50,000 years. At 10% light speed, an enormous technical challenge, the journey would still take 5,000 years. Faster-than-light travel remains firmly in the realm of science fiction. While physicists have explored concepts like warp drives and wormholes mathematically, no known physical principles allow such travel, and the energy requirements would be staggering even if possible. Realistically, Kepler 186f will remain a target for telescopes, not spacecraft, for the foreseeable future. Our best hope for understanding this distant world is through ever more powerful observatories that can analyze its atmosphere and search for signs of life from afar. And that might be enough. If we can detect oxygen and methane in Kepler 186f's atmosphere, we don't need to visit to know life exists there. If we can measure its temperature, map its clouds, determine its composition, we'll understand this world in ways that would have seemed impossible just decades ago. 500 light-years away, in the constellation Cygnus, orbits a planet that changed how we see the universe. Kepler 186f, roughly Earth's size, orbiting in the habitable zone of its star, a world that might, just might, harbor the conditions for life. We don't know if Kepler 186f has oceans or continents, clouds or clear skies. We don't know if it has an atmosphere thick enough to sustain liquid water, or if it's a frozen wasteland. We don't know if life has ever emerged on its surface, in its oceans, or beneath its ground. But we know it exists. We know Earth-sized planets in habitable zones are real, not just theoretical possibilities. We know that worlds resembling our own orbit other stars throughout the galaxy, and that knowledge changes everything. Kepler 186f was the first, but not the last. The Kepler mission discovered thousands of planets, proving that worlds are common, that planetary systems are diverse, and that potentially habitable planets exist in abundance. The universe, we learned, is filled with worlds. The search continues. With every new telescope, every new mission, every new observation, we come closer to answering the profound questions that have haunted humanity since we first looked up at the stars. Are we alone? Is Earth unique? Or is the universe teeming with life? The next time you look up at the constellation Cygnus on a summer night, remember, among those stars, too distant to see with the naked eye, lies Kepler 186, and orbiting that star is a world about the size of Earth, in the habitable zone, waiting to reveal its secrets. Kepler 186f discovered. April 17, 2014 distance, 500 light-years radius, 1.17 Earth radii orbital period, 129.9 days status. First Earth-sized planet confirmed in habitable zone. Next on our list, let's move on to WASP 12b. The extreme world of a hot Jupiter. Kepler 186f showed us hope, an Earth-sized planet in the habitable zone where conditions might be just right for life. But the universe doesn't only create temperate, hospitable worlds. It also creates extremes, planets so extreme they challenge everything we thought we knew about how worlds can exist. What if we told you about a planet so close to its star that it's being torn apart? A world so hot that rocks vaporize in its atmosphere? A gas giant so distorted by gravity that it's shaped like a football, not a sphere? Welcome to WASP 12b, one of the most extreme planets ever discovered. Imagine a world where the dayside temperature exceeds 2,500 degrees Celsius, hot enough to vaporize iron, where the planet is so close to its star that it completes an orbit in just 26 hours, where tidal forces stretch the planet into an egg shape, and where material from the planet's atmosphere streams continuously toward the star in a death spiral. This is WASP 12b, a hot Jupiter pushed to the absolute extreme. It's one of the hottest planets ever discovered, one of the darkest, and remarkably, one of the shortest lived. This planet is being consumed by its star, losing mass at an astonishing rate. In just 10 million years, the blink of an eye in cosmic time, WASP 12b may be completely destroyed. Discovered in 2008, WASP 12b has become one of the most studied exoplanets, a laboratory for understanding extreme planetary physics. It's shown us that planets can exist under conditions far more extreme than we imagined, and taught us how worlds can die. Our story begins with the wide-angle search for planets, WASP, a project designed to hunt for transiting exoplanets using relatively small, ground-based telescopes. Unlike the Kepler mission with its single spacecraft, WASP uses multiple wide-field cameras strategically placed around the globe. WASP North, located at the Roque de los Muchachos Observatory on La Palma in the Canary Islands, began operations in 2004. Its southern counterpart, WASP South, started observations from Sutherland, South Africa, in 2006. Together, These robotic cameras monitor millions of stars every night, searching for the telltale dimming caused when a planet transits across its star. The WASP project takes a different approach than missions like Kepler. Rather than staring continuously at one patch of sky, WASP surveys large areas, monitoring bright stars that are easier to follow up with other telescopes. When WASP detects a transit candidate, larger telescopes confirm the discovery and characterize the planet. In 2008, WASP detected periodic dimming in a star cataloged as WASP-12, located approximately 1,400 light-years away in the constellation Auriga, the Charioteer. The star is Sun-like, slightly more massive, slightly hotter, but fundamentally similar to our Sun. The dimming pattern indicated a Jupiter-sized planet orbiting extremely close to the star. Follow-up observations using the radial velocity method confirmed the planet's existence and measured its mass. The team, led by Leslie Hebb and her colleagues, announced the discovery on April 1, 2008. But there was nothing foolish about this find. WASP-12b was immediately recognized as extraordinary. The planet's orbital period was just 1.09 days, 26 hours. It orbited at a distance of only 3.5 million kilometers from its star, 1/40th the distance between Mercury and our Sun. At this proximity, the planet's day side would be blasted with intense stellar radiation, heating it to extreme temperatures. Within months, dozens of telescopes were trained on WASP-12b. The Hubble Space Telescope, the Spitzer Space Telescope, ground-based observatories around the world. Everyone wanted to study this extreme planet. And with each observation, WASP-12b revealed new surprises. WASP-12b is a planet of extremes. Let's explore what makes this world so extraordinary and so doomed. WASP-12b has approximately 1.4 Jupiter masses, but is nearly twice Jupiter's size in radius, about 1.9 Jupiter radii. This makes it one of the most bloated planets ever discovered, with a density less than 1/8 that of water. It's essentially a huge, puffy ball of gas, inflated by the intense heat from its nearby star. The dayside temperature of WASP-12b reaches approximately 2,500 degrees Celsius, 4,500 degrees Fahrenheit. That's nearly half the temperature of the Sun's surface. At these temperatures, metals vaporize. Titanium, vanadium, iron all exist as gases in the atmosphere. The planet itself glows from thermal emission, radiating more energy at some wavelengths than it reflects from its star. Remarkably, despite its extreme temperature, WASP-12b is one of the darkest planets known. In 2017, astronomers measured its visible light reflectivity, its albedo, and found it reflects less than 6% of the light that hits it. It's darker than asphalt, darker than coal. The planet appears pitch black. Why is it so dark? The extreme temperatures allow atoms and molecules in the atmosphere to absorb visible light very efficiently. Alkali metals like sodium and potassium, present as gases, absorb across a broad spectrum. There are no reflective clouds. Any condensates would instantly vaporize at these temperatures. The light that enters the atmosphere is trapped and absorbed. But the most striking feature of WASP-12b is its shape, or rather, its lack of a spherical shape. The planet orbits so close to its star that tidal forces, the differential pull of gravity across the planet, stretch it into an ellipsoidal shape, like an egg or a football. The planet is noticeably elongated, with its long axis pointing toward the star. The planet is approaching what astronomers call the Roche limit, the distance at which tidal forces would literally tear the planet apart. WASP-12b hasn't quite reached that point, but it's close. The planet fills what's called its Roche lobe, the region of space where the planet's gravity dominates over the star's gravity. WASP-12b completes one orbit every 1.09 days, just over 26 hours. Like all hot Jupiters, it's tidally locked, with one hemisphere perpetually facing the star and the other in eternal darkness. But unlike rocky planets, where tidal locking is relatively straightforward, WASP-12b's extreme proximity causes more complex tidal interactions. The day side, blasted by stellar radiation, reaches 2,500 degrees Celsius. The night side, receiving no direct starlight, is significantly cooler, perhaps 1,500 degrees Celsius, though still incredibly hot by any standard. This extreme temperature gradient drives powerful atmospheric circulation, with winds potentially reaching tens of thousands of kilometers per hour. WASP-12b's atmosphere is unlike anything in our solar system, a hellish realm where familiar materials exist in exotic states and where the chemistry is driven by extreme temperatures and intense radiation. In 2010, the Hubble Space Telescope detected water vapor in WASP-12b's atmosphere, one of the first such detections on an exoplanet. But this isn't water as we know it. At the temperatures on WASP-12b, water exists only as superheated steam, with molecules moving at tremendous speeds, colliding violently. One of the most surprising discoveries came in 2011, when astronomers analyzing the planet's atmosphere found that it's surprisingly rich in carbon relative to oxygen, a carbon-to-oxygen ratio greater than 1. This is unusual. In our solar system, oxygen is more abundant than carbon, but WASP-12b appears to have more carbon. A carbon-rich atmosphere creates exotic chemistry. Instead of water vapor and silicate compounds, you might have methane, carbon monoxide, and carbon dioxide dominating. Instead of rocky minerals, you might have carbides, compounds of carbon with metals. It's a fundamentally different type of world, with a different chemical foundation. At WASP-12b's extreme temperatures, many metals exist as vapors in the atmosphere. Titanium oxide, vanadium oxide, and atomic iron have all been detected or inferred. These metal vapors absorb visible light, contributing to the planet's darkness. On slightly cooler regions, perhaps at higher altitudes or on the night side, these metals might condense into exotic clouds of molten droplets. WASP-12b exhibits what's called a thermal inversion, a layer in the upper atmosphere where temperature increases with altitude opposite to the normal pattern. This is caused by molecules like titanium oxide and vanadium oxide absorbing stellar radiation in the upper atmosphere, heating it directly. It's similar to how Earth's ozone layer creates a temperature inversion in our stratosphere, but far more extreme. Perhaps most dramatically, WASP-12b is losing its atmosphere to space at a catastrophic rate. Observations have detected a huge cloud of material surrounding the planet, hydrogen, helium, and even heavier elements streaming away from the planet's atmosphere, forming a comet-like tail. The mass loss rate is staggering, approximately 189 trillion kilograms per day, or about 6 billion kilograms per second. At this rate, WASP-12b is losing roughly 1 Earth mass every 10 million years. Since the planet is about 1,400 Earth masses, it has perhaps 10 to 14 million years remaining before it's completely consumed by its star. The process is called Roche lobe overflow. Because the planet fills its Roche lobe, the region where its gravity dominates, material from the outer atmosphere can flow over the boundary toward the star. It's like water overflowing the rim of a cup. The star's gravity pulls this material inward, and the planet slowly shrinks. To understand WASP-12b's fate, we must understand its relationship with its star, a relationship that is slowly destroying the planet. WASP-12 is a G-type star, the same type as our Sun, though slightly more massive at about 1.35 solar masses and slightly hotter at 6,300 Kelvin. It's an older star, estimated to be about 2 to 3 billion years old, middle-aged in stellar terms. But its relationship with WASP 12b is anything but typical. The extreme gravitational interaction between star and planet generates tidal heating within the planet. Just as Earth's tides are caused by the moon's gravity, WASP-12b experiences enormous tidal forces from its star. These forces continuously flex and squeeze the planet's interior, generating heat through friction. Astronomers have calculated that WASP-12b emits more energy than it receives from its star. It's slightly brighter in infrared than it should be based solely on absorbed stellar radiation. The extra energy comes from tidal heating and from the planet's gradual contraction as it loses mass. The planet is literally glowing from its own internal heat. In 2017, astronomers announced a startling discovery. WASP-12b's orbit is decaying. By comparing transit timing observations from 2008 to 2017, they found that the planet's orbital period is decreasing by about 29 milliseconds per year. This might not sound like much, but it's observational proof that the planet is spiraling toward its star. The orbital decay is caused by tidal interactions. As the planet orbits, it raises tides on the star, bulges of stellar material that follow the planet. But the star's rotation is slower than the planet's orbit, so the tidal bulges lag behind the planet. This creates drag, gradually slowing the planet's orbit and causing it to spiral inward. At the current rate of orbital decay, WASP-12b will collide with its star in approximately 3.2 million years, incredibly soon in astronomical terms. Combined with the atmospheric mass loss, the planet has perhaps 10 million years remaining in either scenario. We are witnessing the death throes of a world. The material flowing from WASP-12b doesn't simply vanish, it falls onto the star. Hubble observations have detected enhanced magnesium and carbon in the star's outer layers, material that likely came from the planet. In effect, the star is cannibalizing its planet, enriching its atmosphere with the planet's own material. What will ultimately happen to WASP-12b? It might be completely stripped of its atmosphere, leaving only a dense core that eventually plunges into the star. Or it might be torn apart by tidal forces before reaching the star's surface, its material forming a temporary ring around the star before being accreted. Either way, this planet is doomed. WASP-12b's extreme nature makes a uniquely valuable scientific laboratory. Despite, or because of, its extreme conditions, this planet has taught us profound lessons about planetary physics, atmospheric chemistry, and the life cycles of worlds. WASP-12b represents an endpoint in the hot Jupiter population, a planet pushed to the absolute limit of how close a gas giant can orbit its star. By studying this extreme case, we learn about the boundaries of planetary existence, the physical processes that determine where planets can and cannot survive. The planet's extreme inflation, nearly twice Jupiter's radius despite similar mass, has challenged our understanding of planetary structure. What makes WASP-12b so bloated? Is it tidal heating? Stellar irradiation deposited deep in the atmosphere? Chemical processes? Studying WASP-12b helps us understand the mechanisms that inflate hot Jupiters. The discovery of WASP-12b's carbon-rich atmosphere opened a new avenue of research. Most planets in our solar system are oxygen-rich, with carbon-to-oxygen ratios less than 1. But WASP-12b showed that carbon-rich planets exist. This has implications for planetary formation. The carbon-to-oxygen ratio tells us where in the protoplanetary disk the planet formed. A carbon-rich composition suggests WASP-12b formed in the outer regions of its protoplanetary disk, beyond the soot line, where carbon-rich materials could condense. It then migrated inward to its current position. The planet's composition preserves a record of its formation history, like a geological sample preserving Earth's past. WASP-12b's dramatic atmospheric escape, 6 billion kilograms per second, provides a natural laboratory for studying mass loss processes. These same processes affect many exoplanets, particularly those around red dwarf stars. Understanding how and why planets lose their atmospheres helps us predict which planets might retain habitable conditions. The confirmed orbital decay of WASP-12b provides rare observational evidence of tidal evolution in action. While we've long predicted that close-orbiting planets should spiral toward their stars, WASP-12b is one of the few planets where we've actually measured this process. It tests our models of tidal interactions and helps us understand the long-term evolution of planetary systems. WASP-12b's extreme darkness, reflecting less than 6% of incident light, taught us that planets can be much darker than we expected. The mechanisms that make WASP-12b so dark, efficient light absorption by metal vapors and alkali metals, absence of reflective clouds, likely apply to other ultra-hot planets as well. By comparing WASP-12b to other hot Jupiters, some with similar temperatures but different compositions, some with similar orbits but different inflation levels, we build a comprehensive understanding of how planetary properties depend on mass, composition, stellar irradiation, and other factors. WASP-12b is one point in a larger picture. WASP-12b has been observed by virtually every major telescope in operation: ground-based and space-based, optical and infrared, transit observations, and direct emission measurements. Let's explore how astronomers have pieced together our understanding of this extreme world. The Hubble Space Telescope has observed WASP-12b extensively, using both optical and near-infrared spectroscopy. Hubble detected water vapor, measured the planet's albedo, and revealed the extended hydrogen cloud surrounding the planet. Hubble's ultraviolet capabilities allowed detection of heavy elements in the escaping atmosphere. The Spitzer Space Telescope, operating in infrared wavelengths, measured the planet's thermal emission, the heat it radiates. By observing full orbits, Spitzer created thermal maps showing how temperature varies across the planet's day and night sides. These observations revealed the planet's extreme heat and the efficiency of atmospheric heat transport. Large ground-based telescopes like the VLT, Keck, and Gemini have contributed high-resolution spectroscopy, detecting specific atomic and molecular species in the atmosphere. These observations revealed the carbon-rich nature of the atmosphere, detected metal vapors, and measured wind speeds from Doppler shifts. More recently, the James Webb Space Telescope has observed WASP-12b with unprecedented precision. JWST's infrared sensitivity allows detailed characterization of the planet's atmosphere, measuring abundances of water, carbon monoxide, and other molecules with far greater accuracy than previous instruments. By carefully measuring the exact timing of transits over many years, astronomers detected the orbital decay. This requires exquisite precision, measuring when the planet crosses its star to within seconds, then comparing measurements separated by years. The slight shift in timing revealed that the orbit is shrinking. Secondary eclipse observations, when the planet passes behind the star, allow measurement of the planet's thermal emission separately from reflected light. By comparing the system's brightness with and without the planet visible, astronomers determine how much energy the planet emits, revealing its temperature and thermal structure. Phase curve observations track the system's brightness throughout the entire orbit, revealing how the planet's appearance changes as different portions of its day and night sides become visible. These observations map temperature variations across the planet and measure how efficiently the atmosphere transports heat. WASP-12b is extreme, but it's not alone. The universe has created an astonishing variety of bizarre worlds, each extreme in its own way. KLT9b, discovered in 2017, is even hotter than WASP-12b, with dayside temperatures exceeding 4,300 degrees Celsius, hot enough that molecules break apart into individual atoms. It's hotter than many stars. HD 189733b is famous for its deep blue color, not from oceans, but from silicate particles in its atmosphere that scatter blue light. On this planet, it might rain molten glass sideways in 7,000 km/h winds. WASP 76b is hot enough on its day side to vaporize iron. These iron vapors are carried by winds to the cooler night side, where they condense and fall as iron rain, liquid droplets of molten metal falling through the atmosphere. At P 7b might have clouds made of corundum, the mineral that forms rubies and sapphires. It might literally rain gems on this alien world. WASP 12b stands out even in this gallery of extremes. While other planets are hotter or weirder, WASP 12b is unique in its combination of extreme properties: ultra-hot, ultra-dark, ultra-inflated, tidally distorted, losing mass, and spiraling toward doom. It's extreme in multiple ways simultaneously. Together, these extreme worlds teach us that hot Jupiters are incredibly diverse. Some are hot, some are ultra-hot, some are bright, some are dark. Some have clear atmospheres, some have thick clouds. This diversity reflects differences in composition, formation history, and stellar environment. WASP 12b's fate is sealed. This world, which has existed for billions of years, has only millions of years remaining. What will its final chapter look like? Today, WASP 12b continues its doomed orbit, losing mass at 6 billion kilograms per second, spiraling slowly toward its star. Each year, the orbital period decreases by 29 milliseconds. Each year, the planet edges slightly closer to destruction. Over the next few million years, the atmospheric mass loss will continue. The planet will grow smaller, less massive, less inflated. The escaping material will continue to rain onto the star, enriching its atmosphere with the planet's substance. As the orbit decays and the planet moves closer to the star, tidal forces will intensify. Eventually, perhaps in just a few million years, the planet will cross the Roche limit, the point where tidal forces overcome the planet's self-gravity. What happens then? The planet will be pulled apart by tidal forces, its material forming a ring around the star. This ring will gradually spiral inward, eventually falling onto the star's surface over thousands or millions of years. Alternatively, if the planet has a dense core, perhaps made of heavy elements, water ices, or rocky material, this core might survive the atmospheric loss. As the gaseous envelope is stripped away, a small, dense object might remain, plunging into the star in a final death dive. Will humans witness WASP 12b's destruction? Almost certainly not. The final stages are millions of years away. But if our species and our technology survive long enough, future astronomers might observe the planet's final orbit, watch it cross the Roche limit, and see it torn apart. It would be a spectacular cosmic event, visible across thousands of light years. After WASP 12b is destroyed, what will remain? The star will continue shining, enriched with material from its former planet. The inner planets, if they exist beyond the 4 confirmed, will continue orbiting. But WASP 12b will be gone, consumed by the star it once orbited, its existence recorded only in our scientific archives. 1,400 light-years away, in the constellation Auriga, a planet is dying. WASP 12b, a world 1.5 times the mass of Jupiter, inflated to twice Jupiter's size, heated to 2,500 degrees Celsius, spirals inexorably toward its star. Every second, 6 billion kilograms of the planet's atmosphere flows toward the star. Every year, the orbital period shrinks by 29 milliseconds. Every million years, the planet loses 1 Earth mass. It is a slow-motion catastrophe, a planetary death playing out over cosmic timescales. Yet from this tragedy, comes knowledge. WASP-12b has taught us that planets can exist under conditions far more extreme than we imagined. It's shown us that worlds can be dark as coal, inflated to impossible sizes, enriched with carbon instead of oxygen. It's revealed the processes by which planets lose their atmospheres and spiral to their doom. WASP-12b reminds us that the universe creates worlds of astonishing variety, not just temperate, Earth-like planets in habitable zones, but also extremes we can barely comprehend. Gas giants raining molten iron, planets hotter than stars, worlds being torn apart by tidal forces. In the cosmic cycle, planets are born from clouds of gas and dust, exist for billions of years, and eventually die, colliding with other planets, ejected from their systems, consumed by their stars, or destroyed when their stars expire. WASP-12b's death is not unique. It's simply one of countless worlds meeting their end in the universe every day. But for now, WASP-12b still exists. It still orbits its star every 26 hours. Its atmosphere still boils away into space. Its distorted shape still testifies to the immense gravitational forces at play. For a few million years more, this remarkable world continues its doomed dance. The next time you see the constellation Auriga on a winter night, remember, among those stars shines WASP-12, and orbiting that star is one of the most extreme planets we've ever discovered. A world pushed to the limits of planetary existence, teaching us through its destruction and reminding us that in the universe, even planets are mortal. For our next and final planet for today, we are unveiling K2-18b, the promising exoplanet in the habitable zone. WASP-12b showed us the extreme, a planet pushed to the absolute limits of existence, a world being consumed by its star. But the universe also creates gentler worlds, planets orbiting at temperate distances where conditions might be just right for life. What if we found a planet in the habitable zone where we could actually detect its atmosphere, where we found not just water vapor, but possibly, just possibly, signs of life itself? Welcome to K2-18b, a world that made headlines in 2023 with a discovery that shook the scientific community. Potential evidence of biological activity on a planet 124 light-years from Earth. Imagine a world larger than Earth but smaller than Neptune, orbiting a cool red dwarf star in the constellation Leo. A planet where water vapor hangs in the atmosphere, where temperatures might allow liquid water oceans beneath thick clouds, and where, according to controversial but tantalizing data, a gas called dimethyl sulfide might exist. On Earth, dimethyl sulfide is produced primarily by ocean phytoplankton, living organisms. If it exists on K2-18b, it could be our first detection of a biosignature on an exoplanet, a chemical sign of life on another world. This is K2-18b, and its story is still being written. In September 2023, scientists announced that the James Webb Space Telescope had detected possible traces of dimethyl sulfide in K2-18b's atmosphere. The news made headlines worldwide, but the discovery is controversial, the evidence uncertain, and the debate fierce. Is K2-18b a living world, or are we seeing what we desperately want to see? Our story begins with redemption. In 2013, NASA's Kepler Space Telescope suffered a mechanical failure when two of its four reaction wheels, devices that control the spacecraft's pointing, failed. The primary Kepler mission, which had revolutionized our understanding of exoplanets, seemed over. But NASA engineers devised a clever solution. By using solar pressure as a virtual third reaction wheel, Kepler could still point accurately, though would need to observe different fields along the ecliptic plane. The K2 mission was born, a second chance for Kepler to discover new worlds. During campaign 1 of the K2 mission in 2015, Kepler observed a star cataloged as EPIC 2019125552, later designated K2-18. Located 124 light-years from Earth in the constellation Leo, the star is an M-dwarf, a red dwarf about one-third the mass of our Sun and much cooler and dimmer. The data revealed a clear transit signal, a periodic dimming indicating a planet passing in front of the star. The planet, designated K2-18b, had a radius about 2.6 times Earth's radius, making it a super-Earth, larger than our planet but smaller than Neptune. But what made this discovery special was the planet's orbital period, 33 days. With a 33-day orbit at approximately 0.14 AU from its star, about 1/7 Earth's distance from the Sun, K2-18b receives about 35% of the energy flux that Earth receives from our Sun. Given the star's lower temperature and luminosity, this places K2-18b squarely within the habitable zone, the region where liquid water could exist on a planet's surface. The discovery was announced in 2015, but K2-18b was just one of thousands of planets found by the K2 mission. Initially, it didn't receive special attention. That would change a few years later when astronomers began studying its atmosphere. In September 2019, two independent research teams announced a groundbreaking discovery. They had detected water vapor in K2-18b's atmosphere using the Hubble Space Telescope. It was the first detection of water in the atmosphere of an exoplanet orbiting in the habitable zone. The news made headlines worldwide. K2-18b became one of the most famous exoplanets, featured in countless news articles, documentaries, and science programs. Here, finally, was a temperate planet with water vapor, an essential ingredient for life. But detecting water vapor was just the beginning. The real question was, what else might be in that atmosphere? To understand K2-18b, we must first understand its cosmic home, the K2-18 system, dominated by a small red dwarf star and its intriguing planets. K2-18 is an M2.5 dwarf, a cool red dwarf star with about 37% of the Sun's mass and just 3.5% of the Sun's luminosity. Its surface temperature is approximately 3,500 Kelvin, compared to our Sun's 5,800 Kelvin. The star glows with a deep orange-red light, emitting most of its energy in the red and infrared portions of the spectrum. K2-18 lies 124 light-years from Earth in the constellation Leo, the Lion. That's about 30 times farther than Proxima Centauri, but still relatively close in galactic terms. Light leaving K2-18 today began its journey around the year 1900 during the reign of Queen Victoria. K2-18 is an old, quiet star, estimated to be several billion years old, possibly older than our Sun. Unlike many young red dwarfs that produce violent flares and intense magnetic activity, K2-18 is relatively calm. This is crucial for habitability. A quiet star is less likely to strip away planetary atmospheres with radiation. The K2-18 system contains at least 2 known planets, both detected through transits. Let's meet them. K2-18c is the inner planet, orbiting at approximately 0.09 AU with a period of about 9 days. With a radius roughly 1.9 times Earth's, it's likely a mini Neptune or a large rocky planet. It orbits too close to the star to be in the habitable zone. Surface temperatures would be far too hot for liquid water. K2-18b is the outer planet and the star of our story. Orbiting at 0.14 AU every 33 days, it resides comfortably in the habitable zone. But there's been a long-standing mystery about K2-18b. What kind of planet is it? Some data suggest there might be a third planet in the system, but it hasn't been confirmed. The gravitational interactions between K2-18b and K2-18c are complex, making it challenging to detect additional planets. K2-18b is classified as a super-Earth, a planet larger than Earth but smaller than Neptune. But this classification hides a profound mystery. What is K2-18b actually made of? Is it a large rocky planet like Earth, a mini Neptune with a thick hydrogen atmosphere, or something entirely different, a type of world that doesn't exist in our solar system? K2-18b has a radius approximately 2.6 times Earth's radius. Transit observations tell us this quite precisely. Its mass, determined through radial velocity measurements and gravitational interactions, is approximately 8.6 Earth masses. This gives K2-18b a density of about 2.7 grams per cubic centimeter, less than Earth's 5.5 grams per cubic centimeter. What does this density tell us? If K2-18b were made entirely of rock and iron like Earth, it would be much denser. The lower density suggests the planet contains significant amounts of water, ice, or hydrogen and helium gas, or some combination of these. There are three main scenarios for K2-18b's composition. First, it could be a large rocky planet with a thick hydrogen-helium atmosphere, similar to a mini Neptune. Second, it could be a water world with a global ocean hundreds of kilometers deep and possibly a substantial atmosphere. Third, it could be what's called a Hycean world, a new category of planet. A Hycean world, the name combines hydrogen and ocean, is a hypothetical type of planet with a liquid water ocean beneath a thick hydrogen atmosphere. These worlds would be larger and cooler than typical gas giants, but could still maintain liquid water under the right conditions. K2-18b is one of the leading candidates for a Hycean planet. The planet's equilibrium temperature, the temperature it would have based on stellar heating alone, is approximately 250 to 300 Kelvin, or minus 23 to plus 27 degrees Celsius. But the actual surface temperature depends critically on the atmosphere. A thick atmosphere with greenhouse gases could warm the planet substantially. At 0.14 AU from a red dwarf, K2-18b is likely tidally locked, one hemisphere always facing the star, the other in perpetual darkness. This creates extreme day-night temperature differences, though a thick atmosphere would redistribute heat, moderating the extremes. What would it be like to stand on K2-18b if it has a surface at all? The gravity would be noticeably stronger, about 2.6 times Earth's gravity, meaning you'd weigh 2.5 times your Earth weight. The star would appear about half the size of our sun, but would glow deep orange-red. The sky might be hazy from a thick atmosphere, and the light would be dimmer than on Earth. If K2-18b is a water world, there might be no land at all, just a global ocean extending hundreds of kilometers deep. The ocean floor might be exotic high-pressure ice, different from ordinary ice, formed under the immense pressure of all that water. Between the ocean and the thick atmosphere above, any life would exist in an environment utterly alien to anything on Earth. The breakthrough came in 2019, when two independent teams of astronomers analyzed Hubble Space Telescope observations of K2-18b. What they found would make this planet one of the most famous exoplanets in the world. Using transmission spectroscopy, analyzing starlight that passes through the planet's atmosphere during transits, the team searched for the chemical fingerprints of molecules in the atmosphere. And they found what they were looking for: water vapor. Water vapor, H2O molecules in gaseous form, was definitively detected in K2-18b's atmosphere. This was the first detection of water in the atmosphere of a planet orbiting in the habitable zone of its star. On Earth, where there's water, there can be life. Could the same be true on K2-18b? The detection was exciting, but scientists were careful to temper expectations. Water vapor in the atmosphere doesn't mean liquid water on the surface. And even if liquid water exists, that doesn't guarantee life. But it was a crucial first step. K2-18b had at least one of the essential ingredients. In 2023, the James Webb Space Telescope, the most powerful space observatory ever built, turned its gaze to K2-18b. JWST's infrared capabilities allowed far more detailed atmospheric analysis than Hubble could provide. The results were stunning and controversial. JWST confirmed the presence of water vapor and carbon dioxide in the atmosphere. It detected methane, a simple organic molecule. All of this matched predictions for a Hycean world with a hydrogen-rich atmosphere over a water ocean. But then came the controversial finding. In September 2023, astronomers announced they had found tentative evidence for dimethyl sulfide, DMS, in K2-18b's atmosphere. This molecule, with the chemical formula C2H6S, is significant for one compelling reason. On Earth, DMS is produced almost exclusively by living organisms, particularly ocean phytoplankton. Could the DMS on K2-18b be a biosignature, a sign of life? The possibility ignited worldwide excitement. News headlines proclaimed potential signs of life found on distant planet. But the scientific community urged caution. The DMS detection is tentative. It's at the edge of JWST's detection capabilities, and the signal is weak. Other molecules could produce similar spectral features. Statistical analysis shows the detection is uncertain. As one researcher put it, we need more data before we can say anything definitive. Even if DMS is confirmed, proving it comes from life is extraordinarily difficult. We need to rule out all non-biological sources. We need to detect multiple biosignatures in combination, perhaps oxygen with methane, or other gases that shouldn't coexist without biological processes continuously replenishing them. Some scientists propose that K2-18b's atmosphere could be produced entirely by non-biological chemistry, volcanic outgassing, atmospheric photochemistry, geological processes. Others argue that the planet might not have a surface at all, but instead have a thick hydrogen atmosphere extending down to a liquid metallic interior, making it uninhabitable despite being in the habitable zone. K2-18b has brought renewed attention to a radical idea: Hycean worlds, a new category of potentially habitable planet that doesn't exist in our solar system. Hycean worlds are theorized to be super-Earths or mini-Neptunes with thick hydrogen atmospheres overlying global liquid water oceans. They're larger than Earth, with stronger gravity, but the ocean beneath the hydrogen atmosphere could still be habitable, particularly if the pressure and temperature are right. Here's why Hycean worlds are exciting. They might be far more common than Earth-like planets. Mini-Neptunes and super-Earths are abundant in our galaxy, and some fraction might have the right conditions to be Hycean worlds. If life can exist on Hycean planets, potentially habitable worlds might be incredibly common. Hycean worlds could also expand the habitable zone. The thick hydrogen atmosphere provides insulation and greenhouse warming, meaning planets farther from their stars than traditional habitable zones could still have liquid water. Conversely, planets closer to their stars might remain cool enough if they have high albedo, reflectivity, and efficient heat redistribution. But there are challenges. The immense atmospheric pressure at the ocean surface could be hundreds or thousands of times Earth's atmospheric pressure. The hydrogen atmosphere would likely be toxic to life as we know it, and the ocean might be so deep that no light penetrates, eliminating photosynthesis as an energy source. However, life might not need sunlight. On Earth, hydrothermal vents on the ocean floor support thriving ecosystems in complete darkness, using chemical energy instead. A Hycean world might have similar vent systems powered by geological activity or tidal heating. Is K2-18b actually a Hycean world? The atmospheric composition, hydrogen, water vapor, methane, carbon dioxide, is consistent with the hypothesis. The size and density match. The temperature seems right, but we don't know for certain. Alternative explanations, that it's a mini Neptune with no ocean or a water world without a thick hydrogen atmosphere, remain possible. The scientific community is divided about K2-18b. Is it a potentially habitable Hycean world with oceans and possibly life? Or is it an uninhabitable mini-Neptune with a thick hydrogen atmosphere and no surface? Let's explore the debate. Those who believe K2-18b could be habitable point to several factors. It's in the habitable zone. It has water vapor in its atmosphere. It shows methane and carbon dioxide consistent with a Hycean composition. The tentative DMS detection could be a biosignature, and computer models show that Hycean worlds can maintain liquid water. Skeptics counter that the planet's size and mass suggest it might have a thick hydrogen envelope extending deep into the planet, with no distinct ocean surface. That the atmospheric pressure might be too high for life, that the DMS detection is uncertain and could be instrumental noise, and that non-biological processes could explain all the observed molecules. Another concern is stellar radiation. Red dwarf stars, even quiet ones like K2-18, produce ultraviolet radiation and occasional flares that could damage biological molecules on a planet's surface. Without a protective ozone layer or magnetic field, any life would need to shelter deep underwater or develop extreme radiation tolerance. The mini-Neptune scenario suggests K2-18b is more like Neptune or Uranus, a gas planet with a small rocky core, a thick icy mantle, and a massive hydrogen-helium atmosphere. In this scenario, there's no surface to speak of, just increasing density and pressure as you descend. Life as we understand it couldn't exist. The water world scenario proposes that K2-18b has a relatively thin atmosphere, not primarily hydrogen, over a deep global ocean. This might be more habitable than a Hycean world, with lower atmospheric pressure and possibly photosynthetic life in the upper ocean layers. But this model requires the planet to have lost most of its primordial hydrogen, which is difficult to explain. To resolve the debate, we need more data. We need to measure the atmospheric composition more precisely. We need to determine if there's a clear boundary between atmosphere and ocean, or if the planet is gaseous all the way down. We need to search for more biosignatures and rule out non-biological explanations. And we need more powerful telescopes to see details we can't currently detect. K2-18b has become one of the highest priority targets for atmospheric studies. What will future observations reveal? The James Webb Space Telescope will continue observing K2-18b, accumulating more data to confirm or refute the dimethyl sulfide detection. Multiple transits observed with different instruments and techniques will help distinguish real atmospheric signals from instrumental artifacts. Scientists are developing comprehensive biosignature strategies. They're looking not just for individual molecules, but for combinations that would be hard to explain without life. Oxygen and methane together. Oxygen and phosphine. Dimethyl sulfide with other organic sulfur compounds. The key is finding chemical disequilibrium, gases that shouldn't coexist unless something is continuously producing them. K2-18b isn't the only Hycean candidate. Astronomers have identified dozens of other super-Earths in habitable zones that might be similar. By comparing K2-18b to other potential Hycean worlds, some hotter, some cooler, some larger, some smaller, we can test the Hycean hypothesis and understand which conditions actually support habitability. Future space missions could revolutionize our study of K2-18b. NASA's proposed Habitable Worlds Observatory, designed specifically to characterize potentially habitable exoplanets, could image K2-18b directly, separating its light from the star's glare. This would allow unprecedented atmospheric analysis and possibly direct detection of biosignatures. Ground-based extremely large telescopes. The European Extremely Large Telescope, the 30-meter telescope, the Giant Magellan Telescope will also contribute. With mirrors 25 to 40 meters in diameter, these giants will have the resolution and light-gathering power to study K2-18b's atmosphere in exquisite detail. Within the next decade, we'll likely know definitively whether K2-18b has dimethyl sulfide in its atmosphere. We'll have much better constraints on its composition, Hycean world, mini-Neptune, or water world. We might detect additional biosignatures, or confirm that non-biological processes explain everything we see. Either way, we'll learn something profound about this mysterious planet. K2-18b represents a turning point in the search for life beyond Earth. For the first time, we're not just speculating about life on other worlds. We're actually analyzing the atmospheres of potentially habitable planets, searching for signs that life might exist there right now. For decades, the search for extraterrestrial intelligence focused on radio signals from advanced civilizations. But K2-18b represents a different approach, searching for biosignatures, chemical evidence of life, in planetary atmospheres. We're not looking for beings who can communicate. We're looking for any life, from simple microbes to complex ecosystems. If dimethyl sulfide or other biosignatures are confirmed on K2-18b, it would be one of the most important scientific discoveries in human history. It would prove that life arose independently at least twice in the universe. And if life arose twice, it likely arose countless times. The universe might be teeming with life. Conversely, if the biosignatures turn out to be false alarms, produced by non-biological chemistry, that teaches us something crucial too. It tells us we need to be more careful about claiming biosignature detections. It refines our understanding of what atmospheric chemistry looks like on mini-Neptunes and super-Earths. And it reminds us that the search for life requires patience and rigor. K2-18b is one of hundreds of potentially habitable exoplanets we've discovered. Some orbit red dwarfs like K2-18b. Others orbit sun-like stars. Some are Earth-sized. Others are super-Earths or mini-Neptunes. Together, they form a population we're only beginning to understand. K2-18b is special not because it's unique, but because it's accessible, close enough and bright enough for detailed study. Even if K2-18b turns out to be lifeless, even if we study hundreds of potentially habitable planets and find no signs of life, that result would still be profoundly important. It would suggest that life is rare, that Earth is special, that the conditions for life are more stringent than we thought. That knowledge would shape how we view ourselves and our responsibilities to our own planet. 124 light-years away, in the constellation Leo, orbits a planet larger than Earth but smaller than Neptune. It has water vapor in its atmosphere, methane, carbon dioxide, and possibly, just possibly, dimethyl sulfide, a molecule that on Earth is produced by life. We don't yet know what K2-18b really is. A Hycean world with a global ocean beneath a hydrogen sky? A mini-Neptune with no surface at all? A water world with an atmosphere of steam? The evidence is incomplete, the debate ongoing, the answers uncertain. But we're searching. Every new observation brings us closer to the truth. The James Webb Space Telescope continues watching, accumulating data, refining measurements. Future telescopes, even more powerful, are being designed and built. Within our lifetimes, we may know definitively whether K2-18b harbors life. K2-18b reminds us that the question, "Are we alone?" is no longer purely philosophical. It's a scientific question we can actually investigate. We have the technology to detect atmospheres on distant worlds. We can identify molecules that might be produced by life. We can search for biosignatures on planets orbiting other stars. The next time you see the constellation Leo on a spring night, remember, among those stars shines K2-18, and orbiting that star is a world with water in its atmosphere, a world in the habitable zone, a world that might, just might, be telling us that we are not alone. If you made it all the way through this video, thank you so much. It really does mean all the worlds to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.